Hey guys, tonight we travel back to a time before the first word, before the first thought that could be packaged into a sentence, to witness the birth of the single most powerful tool our species has ever invented. Close your eyes and picture it. You're standing in a forest so dense and humid, the air feels like a warm, wet towel on your face. Steam rises from a carpet of rotting leaves, and the air thrums with the screech of insects the size of your hand. This is Africa, but not an Africa you'd recognize. This is the Miocene epoch, millions of years before the first human. And a quick reality check. In this world, with your slow, soft body and dull senses, you probably won't survive this episode, let alone the night. You're not the clever ape here. Not yet. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. That small click sends a big signal to the algorithm. That long-form, serious educational content still matters. And to me, it's an incredibly meaningful show of support. Thank you so much for helping keep this channel going strong. If you feel like it, post your city and the time of night in the comments. It's always cool to see where everyone is tuning in from. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're crouched behind a colossal fern, its fronds beaded with moisture. The air is thick with the smell of damp earth, decay, and strange, heavy blossoms. It's loud. Not the sound of a city, but a chaotic, organic symphony of buzzing, chirping, and rustling that never stops. 7 million years ago, the world was a very different place, and you're about to meet one of your oldest, most significant relatives. Through a gap in the leaves, you see them, a group of creatures moving with a fluid, four-limbed gait. They are not quite chimpanzees, not quite human. This is the clan of our last common ancestor. The evolutionary branching point where the path to us and the path to modern chimps and bonobos diverged. Let's listen. What do you hear coming from them? A sudden sharp bark erupts from a scout perched in a fig tree, and the entire group freezes, eyes scanning the canopy. A moment later, a juvenile, having snatched a piece of fruit from its sibling, lets out a pleading whimper as its mother gives a low, guttural grunt of disapproval. A pair of males, seeing off a rival, puff up their chests and let out a pant-hoot chorus that echoes through the trees. This is communication, without a doubt. It's complex, it's socially rich, and it is absolutely vital for their survival. But it isn't language, not as we know it. These sounds, the barks, whimpers, and hoots, are what scientists call signals. They are functionally bound, emotional, and tied directly to the here and now. The bark doesn't describe the eagle circling overhead. It is a raw, instinctive alarm triggered by the sight of that eagle. The whimper doesn't articulate the concept of injustice over a stolen fig. It is the sound of immediate distress. There is a direct, unbreakable line between the stimulus and the response. It's a closed system. You can't use the eagle bark to talk about the eagle you saw yesterday, or to warn about one you might see tomorrow. The communication is powerful, but it's tethered to the present moment. How can we be so sure? After all, sound doesn't fossilize. There are no audio recordings from the Miocene, no preserved voice boxes. Our main line of evidence comes from comparative biology. By meticulously studying the vocal repertoires of our closest living relatives, chimpanzees and bonobos, we can build a model of what our shared ancestor was likely capable of. Modern chimps have dozens of distinct calls for everything from food and predators to greetings and sex. It's a rich system, but after decades of study, No researcher has ever found a chimpanzee combining their alarm hoot for a snake with their food call for bananas to mean, "Hey, don't go near the bananas, there's a snake there." This is the fundamental difference, the vast cognitive canyon between their communication and ours. Their world is one of signals. Our world is one of symbols. A signal has a direct connection to what it represents. A symbol is abstract, arbitrary. There is nothing about the sound of the word snake that is inherently snake-like. We, as a culture, have simply agreed that this particular noise will represent that slithering reptile. This symbolic nature is what untethers language from the immediate present. It's what allows us to talk about yesterday's snake, tomorrow's snake, a mythical snake, or the very concept of snakiness. Scholars still argue about the precise evolutionary moment our ancestors' calls began to shift from being pure signals to incorporating the first glimmer of symbolic meaning. That journey from a reactive grunt to a representative word is the story of us. And it didn't begin with the mouth, but with a toolkit that had been evolving for hundreds of millions of years for entirely different reasons. To understand how those grunts and hoots you're hearing in the Miocene forest eventually become poetry and physics, we have to do something counterintuitive. We have to leave our ape-like ancestors behind for a moment and travel much, much further back. We need to look for the raw materials, the anatomical toolkit that would one day be repurposed for speech. So, let the humid air of the forest dissolve and feel the timeline spool backwards, past the dinosaurs, past the great forests of the Carboniferous, until you find yourself on the muddy shore of a brackish swamp 400 million years ago. The air here is thick, heavy, and low in oxygen. Strange, stubby plants, the planet's first attempt at forests, line the water's edge. There are no birds, no mammals. The only sounds are the lapping of the water and the scuttling of giant, armor-plated insects. You're watching a bizarre creature flop and gasp in the shallows. It looks like a stout, ugly fish, but with fleshy, lobed fins that have the faint beginnings of limbs. This is one of our most ancient grandmothers, an early tetrapod, and she's in the middle of the single most audacious move in the history of life, the invasion of the land. And right now, it's not going well. Her gills, so efficient in the water, are useless here. She's gasping, trying to pull oxygen from the air into a small, internal pouch. This pouch, originally an organ for controlling buoyancy in the water called a swim bladder, is being painstakingly repurposed by evolution. It is the ancestor of your lungs. This is the birth of the engine of language. Not because this creature had anything to say, but because it had a desperate need to breathe. To make this new system work, another innovation was needed. A sheet of muscle developed below these primitive lungs, a muscle that could contract forcefully, creating a vacuum that would actively pull the thin air inside. This was the diaphragm. For this gasping fish creature, it was a biological panic button, a way to power breathe. For you, hundreds of millions of years later, it's the source of the steady, controlled column of air you use to whisper, to shout, to sing, or to hold a single, long note. These are what biologists call pre-adaptations, or more formally, exaptations. It's one of the most beautiful and fundamental concepts in evolution. The idea that a trait evolves for one specific purpose, and then, much later, gets co-opted for a completely different function it just happens to be suited for. Evolution is not a grand designer. It doesn't plan for the future. There was no blueprint that said, Let's develop a diaphragm now so that our distant descendants can argue about politics. The diaphragm was for breathing. The lungs were for breathing. Full stop. But once they existed, they opened up a world of acoustic possibility that was entirely accidental. While you watch our ancestors struggling on the mudflat, consider another piece of the toolkit: the tongue. In fish, the tongue is little more than a bony, immovable nub used to prevent prey from escaping. But on land, you need a way to control the food in your mouth. You need to move it, position it on your teeth, and mash it against your palate before swallowing. So, land animals developed a muscular hydrostat, a boneless, agile sack of muscle, much like an elephant's trunk or an octopus's tentacle. Its original job was purely mechanical, shoving slippery food down the gullet. Its incredible agility and power were adaptations for eating. And yet this fleshy food piston would one day become the master articulator of sound, the anatomical sculptor that shapes the raw vibration from your larynx into the crisp consonants and fluid vowels of speech. The entire physical apparatus of language is a masterpiece of evolutionary reselling. Biologists still argue passionately about the role of exaptation in creating complex systems. Some see it everywhere, arguing that almost every major innovation, from feathers on birds to the bones in our own ears, is a story of repurposing. Others are more cautious, believing it can't explain the whole picture. But for the story of speech, it is undeniable. We didn't evolve a unique speech organ. We took the machine that was built for breathing and eating, and much, much later, our clever primate brains figured out how to play it like a musical instrument. But having the instrument is only half the story. The neurological software to control it was still a long way off. In fact, the first sparks of that linguistic software might not have controlled the mouth at all. They may have been focused on something else our ancestors were just starting to get a grip on: their newly freed hands. Let's spool the timeline forward again, leaving the gasping tetrapod on its muddy shore and traveling ahead more than 350 million years. The camera settles in the lush, dripping canopy of a treetop world in what will one day be Egypt, around 30 million years ago. You're perched on a branch, much smaller now, covered in fur, with a long tail for balance. You are an early primate, maybe something like Egyptopithecus, and your world is a three-dimensional matrix of branches, vines, fruits, and dangers. You live in a noisy, competitive, and intensely social troop. And to navigate this world, you need to communicate constantly. You still have a repertoire of hoots and calls, much like the ones we heard from our later relatives in the Miocene. They are essential for broadcasting warnings over long distances. But here, up close, in the intimate space of the troop, you can see another, richer channel of communication at play. Watch the dominant male. He doesn't need to make a sound to get his point across. A narrowed gaze and a tense posture are enough to make a subordinate drop a prized piece of fruit. See a mother gently beckon her infant closer with a slight curl of her fingers. Observe two individuals meticulously grooming each other, their hands speaking a language of social bonds, trust, and reciprocity. This is a world of gesture. This observation is the bedrock of a compelling and powerful idea about our own origins, the gesture-first hypothesis. It's one side of a long-standing scholarly debate about the roots of language. While some researchers argue that our language evolved in a direct line from primate vocal calls, others propose a more radical theory, that for millions of years, our ancestors' communication was primarily manual and visual. They suggest we went through a long, silent movie phase, where the first truly complex, symbolic ideas were not spoken, but signed. The logic is elegant. Unlike the innate, emotionally driven vocal calls for things like danger or food, gestures are inherently more flexible and iconic. You can use your hands to trace the shape of the thing you want to talk about, to point towards a location, to mimic an action. A gesture can be a simple representation, a tiny step away from a pure signal and towards a true symbol. For decades, this was a fascinating but largely speculative idea. Then, in the 1990s, a team of Italian neuroscientists made a startling discovery while studying the brains of macaque monkeys. They found a unique class of brain cells which they named mirror neurons. And these neurons did something remarkable. When a monkey reached out and grasped a peanut, a specific neuron in its premotor cortex would fire. That was expected. The surprising part was that the very same neuron would also fire when the monkey simply watched another monkey, or a human researcher, perform the exact same action. Your brain, it turns out, simulates the actions of others. This discovery was a potential Rosetta Stone for understanding the neurology of social connection. These mirror neurons create a bridge between doing and seeing, a shared neural space where your action is automatically and effortlessly mapped onto the part of my brain that produces my action. They are the reason you might wince when you see someone trip, or feel a ghost of the sensation when you watch a friend take a cool drink on a hot day. For proponents of the gesture-first theory, this was the smoking gun. What could be a more perfect neural mechanism for a language based on gesture? This system allows for a seamless understanding of actions and, by extension, the intentions behind them. It's a natural platform for learning by imitation and for building a shared vocabulary of meaningful signs. Now, connect this back to our own family tree. For all the primates in this Oligocene forest, their hands are still very much occupied with the business of walking and climbing. Gestures are fleeting, used only when paused on a branch. But millions of years later, on the expanding savannas of Africa, your ancestors will make a pivotal change. They will rise up and begin to walk on two legs. We often frame bipedalism as the great liberator of the hands for tool use, and that is certainly true, but it was also the great liberator of the hands for communication. Suddenly, this incredibly sophisticated gestural system, underpinned by a mirror neuron network, was available full-time. The hands were now free to talk, to describe, to plead, to argue, to tell stories in the air. The expressive potential would have been enormous. Our next ancestor, the famous Lucy, walked this new, upright path. Her hands were free, but as we'll see, her voice was still very much trapped in the past. The timeline scrolls forward, and you find yourself in the dry, scrubby landscape of Hadar, Ethiopia, 3.2 million years ago. The world is changing. The dense, continent-spanning forests are retreating, giving way to a patchwork of open savanna and woodlands. It's in this shifting world that you finally meet her. She is small, barely 3.5 feet tall, but she is walking towards a stand of acacia trees on two legs. This is Australopithecus afarensis, and this particular fossil, discovered in 1974, would be nicknamed Lucy. As you watch her, you can see she is a creature of two worlds. Her hips and legs are clearly adapted for upright walking, but her long, powerful arms and curved fingers are a clear inheritance from a tree-dwelling past. She is a perfect transitional form, and as she walks, her hands swing free. They are available for carrying things, for digging, for gesturing, for communicating in that rich, visual language we imagined earlier. She embodies the freedom that bipedalism offered. But what about her voice? We know her hands were free to talk. Was her mouth? Let's get closer and imagine what she might have sounded like. Could she have leaned over to her child, hiding from a predator, and whispered words of comfort? The answer, buried deep in the architecture of her skeleton, appears to be a definitive no. The key lies not in her mouth, but in her neck. In modern adult humans, the larynx, or voice box, sits low in the throat. This creates a large, resonant chamber above it called the pharynx. Think of your vocal tract like a two-part musical instrument. The long tube of your throat and the horizontal tube of your mouth can work together to modify sounds in incredibly complex ways. It's like having a trombone slide connected to a trumpet bell. The range of possible notes is huge. Lucy, however, was built differently. Based on the shape of her skull base and comparisons with the other primates, her larynx was positioned high up in her neck, tucked just behind her tongue, almost exactly like a modern chimpanzee's. This arrangement is actually very efficient for some things. It creates a direct, protected airway that makes it much easier to breathe while climbing, and it allows for the production of loud, resonant, and intimidating pant hoots that can carry for miles across the savannah. But acoustically, it's a simple short tube. It's a flute, not a trombone. While paleoanthropologists still debate the exact range of sounds Lucy could produce, the physics are clear. A high larynx severely limits the ability to modify sound and produce the wide variety of distinct vowels and consonants necessary for human speech. The most crucial piece of evidence for this reconstruction comes from a tiny, delicate, and incredibly rare fossil, the hyoid bone. This is a small, U-shaped bone that floats in your neck, not connected to any other bone. It acts as the anchor for your tongue muscles and the scaffold that supports the larynx. Its shape and position are therefore a direct reflection of the vocal anatomy around it. And while we haven't found Lucy's specific hyoid, a 3.3 million-year-old hyoid bone from another Australopithecus afarensis child, discovered at Dikika, Ethiopia, was found. It is unambiguously ape-like. The hardware for complex speech simply wasn't there. Lucy's calls would have been impressive, powerful, and socially meaningful, but they were not the sounds of a creature capable of whispering secrets. Here's a quirky and profound tidbit to put this in perspective. You were born with a larynx in the same high position as Lucy's. For the first few months of your life, your vocal tract was essentially that of an ancient hominin. This ancestral configuration is incredibly useful for an infant, as it allows you to breathe and swallow milk at the same time without choking. It's a critical survival trait. But then, around 3 months of age, something amazing and uniquely human happens. Your larynx begins a slow descent down your throat, moving away from the soft palate and opening up that resonant pharyngeal chamber. This is the moment your body begins to physically build the instrument of speech. But it comes at a terrible cost. This new low position creates a shared passage for both food and air, making adult humans one of the only animals that can easily choke to death on their own food. The fact that evolution made this dangerous trade-off is perhaps the strongest evidence imaginable for how vital complex speech would become for our survival. Lucy stood at the precipice of this change, a bipedal ape with a voice still tied to her arboreal past, ready for the next evolutionary pressure that would demand more than just a gesture and a call. You leave Lucy contemplating her world of silent gestures and loud calls, and you drift forward in time. The African landscape around you grows drier, the woodlands thinner. The easy fruits of the forest are becoming scarcer, and survival now depends on new strategies, new foods, and new ideas. You find yourself on the dusty floor of a great rift valley, a place that will one day be called Olduvai Gorge in Tanzania. It is 2.5 million years ago. Kneeling by a dry riverbed is a creature that looks subtly different from Lucy's kin. Its face is a little flatter, its posture a bit more human, but the most significant change is hidden inside its skull, which is noticeably larger and rounder. This is Homo habilis, the handy man, and it is holding the key to our future. In its hand is a rock. But it's not just any rock. It's an Oldowan chopper, one of the first and most enduring pieces of technology in the human story. To your modern eye, it looks impossibly crude, just a hefty cobble with a few flakes knocked off one side to create a jagged, sharp edge. It's easy to dismiss. Yet this simple object represents a cognitive explosion, a leap in consciousness as significant as the invention of the microchip. This isn't just a case of picking up a convenient branch to use as a club. This is manufacturing. Homo habilis had to select the right kind of raw material, a fine-grained stone like flint or chert that would fracture predictably. They had to find another harder stone to use as a hammer. Then, holding the core in one hand, they had to strike it with the hammerstone at the precise angle and with the exact amount of force needed to shear off a sharp flake. This is not a single action. It's a recipe, a sequence of carefully planned steps. It requires forethought, an understanding of cause and effect, and the ability to hold a mental template of the desired tool in your mind while you work. This is the scientific evidence, preserved in stone, that a more complex mind was at work. And it raises a monumental question. How do you teach this? How is this life-saving technological tradition passed down from one generation to the next for over 1 million years? Here we enter a fierce, scholarly debate. Was it enough to just watch? Could a young Homo habilis learn the art of flint knapping simply through silent imitation? Perhaps, but the process is subtle, and the materials are unforgiving. A slight change in the angle of a strike can be the difference between a perfect cutting flake and a shattered, useless cobble. Many researchers now believe that this increasing technological complexity created the first powerful, sustained evolutionary pressure for a more sophisticated communication system. This is the likely birthplace of proto-language. Imagine the scene. An elder is teaching a novice. Gestures are still paramount. A pointed finger indicates this rock, not that one. A mimed motion shows how to grip the core. But now, perhaps vocalizations are added to the mix. A sharp, guttural sound that means strike. A softer grunt that means hold. Maybe a specific call that identifies the sharp edge. For the first time, sound guides are being deliberately linked to objects and actions. This isn't language for gossiping by the fire or for contemplating the sunset. This is language as a user manual. It's purely functional, concrete, and tied to the immediate task. The sentences are short, barely sentences at all. Give rock. Hit here. Good flake. It's the verbal equivalent of an IKEA instruction sheet. You might even consider the sounds of the process itself as a form of communication. The percussive, rhythmic crack, crack, crack of a skilled napper would have sounded completely different from the dull, clumsy thuds of a beginner. The very acoustics of the work could have transmitted information about technique and success. This constant interplay between hand and eye, between teacher and student, between gesture and sound, created a new kind of cognitive environment. The hand and the tongue were beginning to dance together, and the choreographer for this dance was the growing brain. The neural pathways required for controlling the complex, sequential motor movements of tool-making are remarkably similar to those required for organizing words into a coherent sentence. A new feedback loop was just getting started. Better tools required better communication, which in turn required a bigger brain, which could then invent even better tools. The revolution was no longer just in their hands, it was taking place inside their heads. That feedback loop, the dance between the talking hand and the tool-making tongue, needed a more powerful processor. An evolving culture of technology and communication demands a brain capable of running the increasingly complex software. But this presents a problem for us, peering back through the millennia. Brains, being soft, fatty organs, are embarrassingly bad at becoming fossils. They are among the first parts of the body to decay, leaving behind nothing but an empty, silent skull. So how can we possibly know what the brain of Homo habilis looked like? How can we track the slow awakening of the mind? The answer is that we don't look for the brain itself, but for the ghost it left behind. The solution is a clever piece of scientific detective work using what are called cranial endocasts. Sometimes nature does the work for us, and a skull fills with fine sediment after death, which then hardens into a perfect, fossilized impression of the brain it once held. More often today, scientists use CT scanners to create a high-resolution digital map of the inside of a fossil skull. From this data, they can 3D print a precise model of the brain's size, shape, and surface features. It's like studying a sculptor by examining the inside of the mold they used. You can't see the artist's thoughts, but you can see the shape of their creation. When you place the endocast of a Homo habilis next to that of an earlier ancestor like Lucy, the first difference is obvious. Size. Lucy's brain was about 450 cubic centimeters, not much larger than a modern chimpanzee's. The brain of Homo habilis, however, had swelled to an average of 650 to 700 cubic centimeters. It's a significant leap, a 45% increase, but size is a notoriously blunt instrument. The real magic isn't just about adding more memory. It's about upgrading the wiring. A bigger brain is only useful if its different regions can communicate quickly and efficiently. In modern human brains, this is accomplished by a massive volume of white matter. Fatty nerve fibers that act like fiber optic cables, connecting disparate areas. While we can't see the white matter on an endocast, the changes in the brain's external shape suggest this crucial rewiring was already underway. Our ancestors weren't just getting a bigger hard drive, they were upgrading from dial-up to broadband. And on the endocast of Homo habilis, we see the first hints of where that new processing power was being allocated. Let's look closely at the surface, specifically at the left frontal lobe. Right there, you can see a slight but distinct rounded swelling, a little bump that isn't present on the endocasts of Australopithecines. This area, known as the third inferior frontal convolution, doesn't look like much, but to a paleoneurologist, it's electrifying. This is the location of what, in modern humans, is a vital piece of linguistic hardware. Broca's area. In your brain right now, Broca's area is doing far more than just controlling your mouth. It's a master of sequence and structure. It helps you string words together in the correct grammatical order, and it also becomes active when you perform complex sequential hand movements. The fact that this specific region, the brain's hub for syntax and complex motor control, begins to expand at the exact moment in the fossil record that our ancestors started making sophisticated sequential stone tools is a breathtaking piece of circumstantial evidence. It is the neurological smoking gun. It physically links the act of making a tool with the capacity for making a sentence. Of course, this interpretation doesn't come without controversy. Paleoneurologists argue intensely over these faint impressions. Is that subtle bulge truly a nascent Broca's area, a clear sign of a brain reorganizing itself for language? Or is it, as skeptics suggest, just a slight variation in vascular plumbing, a meaningless bump that we are investing with wishful thinking? The debate is ongoing, but the coincidence in timing is hard to ignore. Something new was happening in the hominin brain. The pressure to create, to manipulate, and, above all, to teach, was beginning to physically sculpt the brain, carving out new neural real estate dedicated to the logic of sequence. This newly organized brain was consuming a huge amount of energy, and to fuel its continued growth, it needed a new and richer source of calories, a source that those first stone tools were perfectly designed to provide. That newly expanding brain, with its burgeoning Broca's area, came with a voracious appetite. Your brain, right now, despite being only about 2% of your body weight, is consuming a staggering 20% of your daily caloric intake. It is the most metabolically expensive organ you own. For Homo habilis, every tiny increase in brain size had to be paid for with high-energy food. A diet of tough roots and fibrous leaves simply wouldn't cut it anymore. So where did the fuel for this cognitive fire come from? The answer lay in the very tools they were creating. Picture the scene. You're hidden in a thicket of acacia trees, looking out onto the sun-scorched savanna. In the distance, a pride of lions is finishing a feast on a large buffalo, their bellies full. They eventually wander off towards a waterhole, and the vultures begin to descend. But between the lions leaving and the main wave of hyenas arriving, a window of opportunity opens. A small band of Homo habilis cautiously emerges from the tree line. For a long time, paleoanthropologists have engaged in a heated debate, arguing whether our ancestors were noble, proficient hunters or marginal, skulking scavengers. The truth is likely a messy combination of both, but in these early days, scavenging the leftovers of superior predators was almost certainly a cornerstone of their survival strategy. They move quickly towards the carcass, their older one choppers in hand. The sharp flakes, which you saw them making earlier, are now put to use, slicing through the thick hide and cutting away scraps of meat the lions left behind. But the real prize, the nutritional jackpot, is yet to come. One of the hominins picks up a large femur, lays it on a flat rock, and using a heavy chopper as a hammer, brings it down with a sharp crack. The bone splits open, revealing the glistening, fatty treasure within. The marrow. This substance, often called Pleistocene butter, is one of the most calorie-dense foods on the planet, a pure shot of energy, lipids, and protein. And for most of the animal kingdom, it's locked away in a bone vault. Hominins, with their simple stone tools, were the only creatures who had found the key. This new high-quality diet of meat and marrow had a profound biological consequence, one explained by a concept known as the expensive tissue hypothesis. The theory posits that you can't afford to have two incredibly expensive organs at the same time. In this case, the trade-off was between the gut and the brain. A long, complex digestive tract, necessary for fermenting and breaking down tough plant matter, is a huge energy drain. But meat and marrow are calorically dense and relatively easy to digest. As our ancestors incorporated more of this high-quality food into their diet, their guts could become smaller and simpler. The enormous metabolic savings from shrinking the digestive system were then reallocated to the only other organ that was screaming for more power: the brain. We began to trade guts for brains. But this new strategy came with a new set of dangers. A fresh carcass is the most desirable piece of real estate on the savannah, and every predator for miles around knows it. Defending that resource from packs of hyenas, lone leopards, or giant swooping vultures is not a job for one individual. It requires a group, and a group that can act in terrifyingly perfect coordination. This is the social pressure cooker. The proto-language that was once a simple user manual for making tools now had to be adapted for high-stakes life-or-death teamwork. Imagine the flurry of communication needed in those few frantic minutes at the kill site. It's a chaotic ballet of cooperation. Gestures and vocalizations must fly back and forth with speed and clarity. You, watch the hyenas. You, drive the vultures off. Bring that big bone here. Look out! The simple proto-language of hit rock has to evolve to include directions, warnings, and commands addressed to specific individuals. Language is no longer just for making things, it's for surviving together. A powerful new feedback loop has now locked into place. Better tools allow access to meat. Meat and marrow fuel a bigger brain. A bigger brain can conceive of better tools and, just as importantly, can manage the more complex social communication required to acquire and defend that meat. It's a self-reinforcing spiral of intelligence, technology, and language. And it was about to launch the next, more ambitious member of our family on a journey that would take them out of Africa and across the entire globe. The engine of that feedback loop, tools, meat, brains, and sociality, hummed for hundreds of thousands of years, and the result of its work was a new and formidable kind of human. You leave the dusty plains of Olduvai and drift forward to a time around 1.8 million years ago. But you're no longer in Africa. You find yourself standing on a riverbank in the Caucasus Mountains, in a place that will one day be called Dmanisi, in the Republic of Georgia. A group of hominins is confidently making its way across the landscape. They are taller than any you've seen before, with long legs and short arms, their bodies proportioned much more like yours. Their faces are still primitive, with a heavy brow ridge, but their foreheads are higher, housing a brain that has once again expanded, now averaging around 900 cubic centimeters. This is Homo erectus, the upright man, and they are the first great explorers of the human family. For the first time in our 6-million-year story, a hominin has walked out of Africa. This migration across continents was not a single, purposeful journey, but a slow, generational expansion, and it presented this species with a relentless series of new challenges. They had to adapt to colder climates, learn to hunt unfamiliar prey, and defend themselves from new predators like cave bears and saber-toothed cats. Faced with these heightened dangers, a powerful selective pressure would have favored an increase in the size of their social groups. There's safety in numbers. A larger group can better defend itself, hunt more effectively, and share information about a wider territory. But while a bigger group solves one set of problems, it creates a new, more subtle one. How do you hold it all together? In a small troop, social life is relatively simple. But as your group size swells to 50, 80, or perhaps even over 100 individuals, you're suddenly living in a complex social city. You need to keep track of a dizzying web of relationships. Who is your ally? Who is your rival? Who owes you a favor? Who holds a grudge against you? Who is a reliable partner? And who is a lazy freeloader? This is a massive cognitive challenge, a social accounting problem of the highest order. And it's this challenge that many believe was the primary driver for the next stage of our brain's expansion. This is the core of the social brain hypothesis, an idea most famously developed by the British anthropologist Robin Dunbar. Dunbar's research revealed a startlingly consistent pattern across all primate species. There is a direct mathematical correlation between the size of a species' neocortex, the wrinkled thinking part of the brain, and the maximum size of their social groups. Your brain, in essence, sets a hard limit on the number of stable relationships you can effectively manage. And to manage these relationships, primates have a go-to tool: social grooming. The act of picking through a companion's fur is far more than just hygiene. It's a powerful social adhesive. It's calming. It builds trust and coalitions, and the slow, repetitive motions release endorphins that create a bond between the groomer and the groomed. But grooming has a critical, unbending limitation. You can only do it to one individual at a time. Dunbar did the math. For a primate to maintain its alliances in a group of, say, 80 individuals, it would need to spend close to half of its waking hours just grooming. At a certain point, it becomes an impossible bottleneck. You can't spend that much time socializing when you also need to find food, avoid predators, and raise your offspring. How then did Homo erectus maintain the cohesion of their larger groups? Dunbar's elegant solution is that they invented a new, far more efficient form of grooming: vocal grooming. Language, in this view, evolved as a way to service multiple social relationships simultaneously. You can't physically groom 3 friends at once, but you can sit with them and have a conversation. The bonding effect is the same, but it's exponentially more efficient. And what was the likely content of this early vocal grooming? The theory suggests it was, for all intents and purposes, gossip. Not in the trivial modern sense, but as the primary mechanism for exchanging vital social information. The conversations of Homo erectus were likely dominated by the mapping of their social world: who was sleeping with whom, who had found a good source of food and shared it, who was proving to be untrustworthy. Far from being a frivolous pastime, gossip was the glue holding their complex new societies together. While anthropologists still debate the relative importance of different pressures, social bonding versus teaching or hunting coordination, the idea that our language evolved to navigate our increasingly complicated social lives is a powerful one. These new, larger groups, bound together by the flow of social information, were now ready for the next great human invention, a place where this vocal grooming could truly flourish: the fireside. The murmur of that vocal grooming, that constant flow of social information binding the group together, needed a proper theater. For most of hominin history, life was dictated by the sun. Daylight was for foraging, hunting, and making tools. Nightfall was a time of immense danger and inactivity. Huddled together in the darkness, listening to the sounds of nocturnal predators, social interaction would have been minimal, fractured by fear and the inability to see one another's faces. To unlock the full potential of their growing social brains, our ancestors needed to conquer the night. And they did it with the most powerful and transformative tool since the first stone chopper: fire. Let's travel to a cave entrance in what is now Israel, about 800,000 years ago. The sun has set, and a profound primal darkness has swallowed the landscape. The air is cold. From your vantage point, the world is a terrifying abyss of unseen things. But then, you see it. A small, controlled flicker of light inside the cave. It's a campfire. This isn't the raging, chaotic front of a wildfire. This is a contained, deliberate, and sustained burn. This is technology. This is the hearth. The immediate practical benefits are revolutionary. First, there is warmth. A fire provides a bubble of artificial climate, allowing these tropical adapted hominins to survive colder nights and push into temperate latitudes in Europe and Asia. Second, there is protection. The flickering light and billowing smoke create a living fence, a wall of intimidation that keeps formidable predators like saber-toothed cats and cave hyenas at a safe distance. The night is no longer their exclusive domain. Third, and perhaps most importantly, fire makes cooking possible. Applying heat to tough tubers and raw meat doesn't just make them taste better, it fundamentally transforms them. Cooking pre-digests food, breaking down tough fibers and neutralizing toxins, which makes it far easier and faster to chew and digest. This released a flood of new, easily accessible calories, giving another massive boost to our energy-hungry brains. Archaeologists can tell this is a controlled fire, not a natural one, by the evidence left behind. At sites like this one, called Gesher Benot Yaakov, they find not just charred wood, but dense clusters of burned stone tools and animal bones concentrated in a specific area. A hearth, in a way that a random wildfire could never produce. But a fierce debate continues among scholars. Did Homo erectus truly master fire, meaning could they create it at will? Or were they merely fire farmers, opportunistically capturing flames from natural events like lightning strikes, then painstakingly keeping that precious ember alive for as long as possible? Whatever the answer, the social consequences of controlling fire were even more profound than the practical ones. The hearth became the anchor of hominin life. It created a powerful magnetic center that drew the group together. And crucially, it extended the day. For the first time, our ancestors had hours of reliable, safe, social time after sunset. The darkness was no longer dead time, it was now prime time. This was the invention of the living room. Imagine the scene. The day's work is done. The group gathers around the flames. The light softens their heavy-browed faces, and for the first time, they can truly see each other's expressions in the dark, allowing for a new layer of non-verbal nuance. The mesmerizing, hypnotic flicker of the fire itself has a psychological effect, inducing a mild, relaxed, trance-like state that would have lowered social barriers and enhanced a sense of communal belonging. This is the perfect stage for the vocal grooming we saw evolve earlier. The social glue of gossip and information exchange could now be applied more thickly than ever before. But something else, something even more significant, is happening here. In the warm bubble of the firelight, safe from the lurking dangers of the night, communication can make a monumental leap. It can detach from the immediate present. The talk is no longer just about the now. It's the perfect time and place to recount the events of the day, to relive the hunt, to describe the strange animal seen by the river. This is the birth of displaced communication, the ability to talk about things that are not right here, right now. It is the beginning of the narrative. The first stories are being told. A series of grunts and gestures can now paint a picture of the past, creating a shared memory and a shared history for the group. This ability to construct a world with words, to relive and analyze past events, is a pivotal step towards the fully symbolic, abstract language we know today. The flickering firelight casts long shadows, and in those shadows, the first stories are told, weaving the past into the present. This new cognitive world, built around a shared narrative, provides the backdrop for the next actor on our stage. We travel forward in time to a period around 430,000 years ago and deep into the earth. you find yourself in the cool, damp darkness of the Cueva Mayor cave system in the Atapuerca Mountains of northern Spain. To get to our destination, you must follow the path that modern paleoanthropologists take, a journey into a truly underworld. You crawl on your belly for nearly half a kilometer through tight, claustrophobic passages. And then, equipped with ropes and harnesses, you lower yourself down a narrow, 13-meter vertical shaft. At the bottom is a small, silent chamber. This is the Cima de los Huesos, the pit of bones. The floor of this chamber is a breathtaking, chaotic jumble of fossils. This single small pit contains the remains of at least 28 different individuals, men, women, and children. They are not Homo erectus. They are a new, more advanced species, Homo heidelbergensis. Taller and more robust than their predecessors, their brains have expanded yet again, now averaging over 1,200 cubic centimeters, well within the low end of the modern human range. These are the likely ancestors of the Neanderthals, and this strange subterranean chamber is one of the greatest fossil treasures on Earth. But what is this place? Archaeologists still fiercely debate the meaning of this strange assemblage of bodies. Was it a catastrophe? A single event where a whole group fell into the pit? The mix of ages makes this seem unlikely. Was it a kind of garbage chute? A place where bodies were unceremoniously discarded? Or was it something more profound? Was this the world's first cemetery? A sacred place where a community deliberately deposited its dead? The discovery of a single beautifully crafted tool amidst the bones, a stunning red quartzite hand axe nicknamed Excalibur, hints at the possibility of ritual, of a symbolic offering to the departed. Whatever the purpose of this pit, its silent inhabitants have a crucial story to tell us about the evolution of language. Hidden amongst the thousands of fossilized bones, scientists found a single, tiny, almost perfectly preserved treasure. It's a bone you will remember, the hyoid. That little U-shaped bone that floats in the neck, anchoring the tongue and supporting the larynx. It is our only direct fossil evidence for the soft tissue anatomy of the vocal tract. And when the Cima hyoid bone was meticulously measured, and compared to those of modern humans and other primates, the results were astonishing. It was not ape-like. It was not like the hyoid of the earlier Australopithecines. This 430,000-year-old bone was, in its shape and its dimensions, completely and unambiguously modern. It falls comfortably within the range of variation you would find in any population of humans living today. The implications of this are profound. This bone tells us that the entire anatomical structure of the vocal tract in Homo heidelbergensis was essentially the same as yours. Their larynx sat low in their throat. They had a large pharynx capable of modifying sound. Their tongue had the same range of motion. The physical instrument for producing clear, rapid, and highly varied speech sounds was fully assembled and in place. The hardware upgrade was complete. This discovery, however, solves one mystery only to create a new, more compelling one. They had the instrument. But did they know how to play it? This is the crux of the issue. A modern vocal tract is necessary for modern speech, but it is not sufficient. You also need the complex neural software in the brain to control it, the fine motor coordination, the grammatical rules, the symbolic thinking. The Cima fossils provide us with a hominin that had the throat of a modern human. But what was going on inside their much larger, but still differently organized brain? We know they were highly effective hunters of dangerous, large game like bison and horses. It is almost impossible to imagine them coordinating such complex, cooperative hunts without an equally complex and efficient communication system. So as you stand in the deep, echoing silence of the pit of bones, you are left to wonder. What did this chamber once echo with? Was it a language of simple, guttural commands? Or were these beings capable of something more? Could they have whispered a eulogy for the bodies they lowered into this dark, final resting place? Let's climb out of that silent, subterranean pit and back into the sunlight of the European Pleistocene. We need to see the owners of those modern-looking hyoid bones in action to understand the world their communication system was built to manage. You find yourself on a cool, grassy plain bordering a large lake in what will one day be Schöningen, Germany. In the distance, a herd of wild horses grazes peacefully. Hiding in the reeds at the lake's edge, you see them. A band of Homo heidelbergensis hunters. They are powerfully built, focused, and they are holding some of the most astonishing artifacts in the human record. They are carrying long, elegant, fire-hardened wooden spears. Discovered in the 1990s, these Schöningen spears, dating back 300,000 to 400,000 years, proved once and for all that these hominins were not just scavengers, but elite, coordinated hunters of large, dangerous game. The spears are perfectly balanced, their tips finely worked, their center of gravity placed exactly where it should be on a modern tournament javelin. This is not a simple ambush. This is a planned, tactical operation. The hunters need to work together with precision to separate a target from the herd and drive it towards a trap or an area where they have the advantage. This level of complex, cooperative action is unthinkable without a correspondingly complex communication system. The simple hit-rock proto-language of Homo habilis is no longer sufficient. So, let's imagine we could listen in. What would we hear? Their language is likely far more advanced. It almost certainly has distinct words for nouns: horse, spear, river, tree, and verbs: run, row, wait, go. They can probably combine them into longer strings with a consistent word order, something like an agent-action-object structure. They can form commands and statements like, "You take spear," "He goes left," "We hunt big horse." You might also hear something that would sound strange to your modern ears. With their fully modern vocal tracts, they had access to a huge range of pitches and tones. Some linguists have proposed that this phase of our evolution was dominated by a musical proto-language, where pitch was as important as the words themselves. A rising intonation at the end of a phrase might signify a question. A sharp, descending tone might be a command. The melody of a sentence could have carried a huge amount of grammatical information, making their speech sound almost like singing. A fluid, melodic, and highly effective language for coordinating action in the physical world. And yet, for all its power, scholars argue that this language was still missing one crucial, almost magical ingredient. It's a property that many linguists, most famously Noam Chomsky, believe is the single defining feature of all modern human languages, the final switch that separates our communication from every other system on the planet. That feature is recursion. Recursion is the ability to embed a phrase or a thought inside another phrase or thought, like a set of Russian nesting dolls. For example, a non-recursive language can handle the sentence, "The horse is big." It can also handle, "We will hunt the horse." But it cannot combine them into, "The horse that is big is the one we will hunt." That little embedded clause, "that is big," is an act of recursion. It allows us to build sentences of infinite complexity and nuance. It lets us talk about the relationships between things, about thoughts about things, about beliefs about thoughts about things. The language of Homo heidelbergensis likely lacked this ability. Their communication was powerful, but linear and flat. It was a superb tool for describing and managing the immediate physical world. It was a language of the here and now, perfectly evolved for the high-stakes ballet of a mammoth hunt. But it probably couldn't handle hypotheticals, counterfactuals, or intricate social reasoning. It could say, "The spear is sharp," but not, "I think the spear that you sharpened yesterday is not sharp enough for this hunt." This leads to a fascinating debate. Were the minds of Homo heidelbergensis simply a less powerful version of ours, or were they operating on a different cognitive software entirely? The absence of recursion might not just be a missing feature, it could represent a fundamentally different way of processing reality. They had pushed proto-language to its absolute zenith. The instrument was perfect, the notes were clear, but they were still playing from a limited songbook. The stage was now set for their descendants to make the final revolutionary leap. As Homo heidelbergensis adapted to the cooling climates of Ice Age Europe, they slowly evolved into their most famous descendants. For over a century, this next character in our story has been a prisoner of popular imagination, a caricature of a brutish, club-wielding, monosyllabic caveman. It's time to meet the Neanderthals as they truly were, a successful, intelligent, and highly complex parallel version of humanity. They thrived across Europe and Western Asia for over 300,000 years, a testament to their incredible resilience and adaptability. But for all their success, the question has always lingered. Could they talk? We know they inherited the modern vocal anatomy of their ancestors. But was that anatomy being put to good use? To find an answer, scientists have recently turned away from the throat and towards another, equally delicate piece of hardware: the ear. The logic is simple and elegant. Language is a two-way street. It's not just about producing sounds, but also about perceiving them with incredible accuracy. If you can't hear the subtle difference between the sounds B and P, then the words bear and pear are meaningless. A sophisticated vocal system is useless without an equally sophisticated auditory system to receive its signals. The challenge, of course, is that the delicate bones of the middle and inner ear are some of the most fragile in the skeleton, and are rarely preserved in the fossil record. But thanks to a few remarkably complete Neanderthal skulls from sites like Atapuerca and in Israel, combined with the power of modern technology, we can now listen in on what the Neanderthals heard. Imagine you are in a sterile white lab, looking over the shoulder of a scientist at a computer screen. On the screen is a ghostly, high-resolution 3D model of a Neanderthal skull. Using micro-CT scanners, which are like medical CAT scans, but on a far more powerful and detailed scale, researchers can digitally dissect the fossil, peeling away layers of bone to reveal the intricate hollow structures within. They can meticulously reconstruct the outer ear canal, the eardrum, and the three tiniest bones in the body: the hammer, the anvil, and the stirrup. These ossicles form a delicate lever system that transmits vibrations from the eardrum to the fluid-filled cochlea of the inner ear. By building a complete digital model of this entire system, scientists can run sophisticated acoustic simulations to calculate precisely how the Neanderthal ear would have responded to different sound frequencies. The results of these studies, published in just the last few years, are a bombshell. The researchers calculated what they call the occupied bandwidth of hearing. Essentially, the range of frequencies where the ear is most efficient and sensitive. What they found is that the Neanderthal auditory system was optimized for the exact same frequency range as your own. But the truly stunning detail was which frequencies their hearing was best at. Their peak sensitivity, the sweet spot of their hearing, was in the range of 2 to 4 kilohertz. This isn't the range for hearing footsteps in the grass or the low growl of a predator. This is the frequency range that contains the specific acoustic information that differentiates consonants, the hard, fast sounds like K, T, P, S, and F that form the backbone of human words. The hearing of other primates, including our old friends the chimpanzees, is not specially tuned to this band. Their communication is mostly based on loud, low-frequency vowels. The high-frequency sensitivity of the Neanderthal ear is a specific adaptation for perceiving speech. This leads to an inescapable evolutionary conclusion, a simple case of use it or lose it. There is absolutely no reason for a species to evolve and maintain the biological hardware for hearing a specific set of sounds if those sounds are not a regular and vitally important part of their acoustic world. An ear so perfectly built to disarm the subtleties of human speech strongly implies the existence of a voice that was producing them. Now, while this evidence is compelling, researchers are quick to point out that hearing capacity doesn't automatically equal linguistic complexity. This data tells us that Neanderthals could almost certainly produce and perceive a wide range of distinct speech sounds, just as we can. It tells us their auditory world was as rich and detailed as ours. But it can't, by itself, tell us if they had mastered recursion or if they could construct the same kinds of complex grammatical sentences. It's another powerful but circumstantial piece of the puzzle. We now know they had the throat to speak and the ears to hear. The case for Neanderthal language is building. The final piece of evidence we need comes not from their bones, but from the blueprint of life itself, their DNA. The evidence from the bones is compelling. The Neanderthals inherited a modern throat from their ancestors and evolved an ear perfectly tuned to the frequencies of speech. The hardware, it seems, was fully installed. But for any complex piece of biological machinery to work, it needs a set of instructions, a blueprint encoded in the very fabric of the organism. To complete the picture of the Neanderthal voice, we have to drill down past the fossils, past the flesh, and into the double helix of their DNA to look for the language gene. Now, I need to be very clear. There is no single gene for language, no magical snippet of code that suddenly granted our ancestors the power of poetry. That's a vast oversimplification. But in the 1990s, scientists did discover a gene that is profoundly and critically linked to our ability to speak. Its name is FOXP2, and the story of its discovery is the story of a single British family, known in the scientific literature only as the KE family. For generations, about half the members of this family had been afflicted by a strange and specific disorder. They had normal intelligence, but they struggled immensely to speak. They had difficulty with the fine, coordinated movements of their lips and tongue required for articulation, a condition called developmental verbal dyspraxia. Their speech was slurred and difficult to understand, and they also had problems with understanding and using grammar. For years, the cause was a mystery. Then, in a landmark study, geneticists were able to trace the family's disorder to a mutation in a single gene on chromosome 7, FOXP2. This was a revolutionary breakthrough. For the first time, a specific gene had been directly linked to specific deficits in speech and language. But what does FOXP2 actually do? It turns out it's not a gene that builds a physical thing, like a protein for a muscle. It's a regulatory gene, which acts like a foreman on a construction site. It controls the activation of a whole network of other genes, telling them when and where to turn on and off during development. Specifically, it plays a crucial role in building the neural circuits in the brain that are responsible for fine motor control and sequencing, exactly the skills you need to produce the rapid, complex, and precise movements of speech. Here's where it gets even more interesting. FOXP2 is not uniquely human. It's an ancient, highly conserved gene found across the animal kingdom. In songbirds, a functioning FOXP2 gene is essential for them to learn and produce their complex songs. In mice, it's involved in their ultrasonic vocalizations and motor learning. In bats, it plays a role in the vocal motor coordination they need for echolocation. Its fundamental job, across species, seems to be related to the learning and execution of complex sequential movements, particularly vocal ones. The human version, however, is slightly different. It contains 2 tiny changes in its amino acid sequence compared to the version found in chimpanzees. These 2 small mutations, which occurred sometime after our lineage split from theirs, appear to have supercharged its function, fine-tuning the neural circuits for the unprecedented motor challenge of human speech. For years, scientists dreamed of being able to ask a simple question. Which version of FOXP2 did a Neanderthal have? Thanks to the almost miraculous technology of ancient DNA sequencing, they got their answer. From a 50,000-year-old Neanderthal bone found in El Cidrón cave in Spain, scientists managed to extract and piece together tiny, degraded fragments of its genetic code. They targeted the FOXP2 gene, and the world of paleoanthropology held its breath. The result was stunning. Neanderthals had the exact same version of the FOXP2 gene that you and I do. They possessed the same 2 key mutations that separate us from chimpanzees. This tells us that the fundamental genetic toolkit for building a brain capable of the fine motor control needed for modern speech was not a recent innovation of Homo sapiens. It was already in place in the common ancestor we share with Neanderthals, a being who lived at least 500,000 years ago. Now, critics, of course, are quick to point out that having the same gene isn't the whole story. The way that gene is regulated and expressed, the volume knob, so to speak, could have been different, controlled by other genes that we haven't yet identified. It's a valid point, a reminder that the picture is always more complex. But the evidence is now a powerful, converging trinity. The modern vocal anatomy inherited from Homo heidelbergensis, the modern auditory system revealed by their ear bones, and now the modern version of the FOXP2 gene, the master switch for vocal motor control. All 3 lines of inquiry point in the same startling direction. The case is no longer about if Neanderthals could speak, but about what they had to say. Let's pause here, in the cold air of a Pleistocene evening, and assemble the case file. For over a century, the Neanderthal has stood trial, accused of being our brutish, silent, and intellectually inferior cousin. It's time to let the modern evidence speak in their defense. Exhibit A is the anatomy. From their ancestors, Homo heidelbergensis, we have a hyoid bone from the pit of bones that is indistinguishable from your own. This is our clearest proof that the physical instrument of the voice, the low-slung larynx and the spacious pharynx, was in place and ready to perform. Exhibit B is the auditory system. From the intricate, digitally reconstructed inner ears of Neanderthal fossils, we know they could hear the world in the same way we do. Their ears were specifically and exquisitely tuned to perceive the high-frequency sounds of consonants that are the backbone of human speech. An ear built to receive speech implies a voice that was producing it. Exhibit C is the genetics. From the faint traces of DNA recovered from their ancient bones, we know Neanderthals carried the exact same version of the FOXP2 gene as modern humans, the crucial regulatory gene involved in the fine motor control and sequencing that makes speech possible. The verdict, based on this powerful convergence of anatomy, audition, and genetics, is now unavoidable. The silent, grunting caveman is a myth. Neanderthals talked. They had a complex vocal communication system, and they used it for hundreds of thousands of years. The great unsettled debate is no longer about if they spoke, but about the content and complexity of that speech. So let's try to imagine it. What would it have been like to hear a Neanderthal speak? First, we should banish the stereotypical low-pitched ugh from our minds. Reconstructions of their vocal tracts, based on their differently shaped skulls, with their enormous nasal cavities, suggest something quite different. Their voices may have actually been higher pitched than ours, and with a distinctly nasal quality. Given their massive chests, they could likely produce sounds with incredible power and volume. Their language was probably highly melodic and tonal, capable of communicating a wealth of practical information about hunts, tool-making, and the environment. But was it truly the same as ours? Could a Neanderthal, if raised in our world, learn to tell a joke? This isn't a frivolous question. A joke is one of the highest achievements of language. It requires far more than just a vocabulary and grammar. To tell a joke, you must possess a sophisticated theory of mind, the ability to accurately model what another person is thinking and what they expect you to say. You then use language to build that expectation and, at the last moment, subvert it in a surprising and humorous way. It is a deeply symbolic act, a sign of a mind that can play with reality, not just describe it. Did Neanderthals have this capacity? To find out, we must look for other signs of symbolic thought in their archaeological record. And here, the evidence becomes more ambiguous, more tantalizing. At a site in Krapina, Croatia, archaeologists found a set of 8 eagle talons, all showing cut marks and polishing that strongly suggest they were once strung together into a necklace or pendant 130,000 years ago. Elsewhere, we find evidence for their use of mineral pigments like black manganese and red ochre. Were they painting their bodies for rituals? And at some sites, we find perforated shells that seem to have been used as beads. These are all flashes of a symbolic, artistic consciousness. But, and it's a big but, these flashes are rare. They are scattered across a vast expanse of time and space. When we compare this sparse record to that of the early Homo sapiens, who will soon arrive on the scene, the difference is stark. We don't find entire cave walls covered in Neanderthal paintings, nor do we find collections of beautifully carved figurines. It's this symbolic gap that gives many researchers pause. It suggests that while Neanderthals spoke, their language may have remained a profoundly practical tool. It was the language of the here and now, a way of managing their physical and social world. But perhaps it never fully untethered itself from reality to build the worlds of myth, art, and elaborate symbolism that would come to define our own species. Their conversations filled the valleys of Ice Age Europe for millennia, but whether they ever used that language to ask why, that is a question whose answer is likely lost to time. While the Neanderthals were holding their own in the cold landscapes of Ice Age Europe, a new story was beginning to unfold back in the African motherland. Let's leave the mystery of the Neanderthal voice hanging in the chilly air and travel back south, to the continent where it all began. Our own species, Homo sapiens, evolved here. The latest fossil discoveries, like the remarkable skulls from Jebel Irhoud in Morocco, push the date of our origin back to at least 300,000 years ago. For a very long time, these early humans were anatomically modern. They looked like us, but their behavior, judged by the stone tools they left behind, seemed little different from that of Neanderthals or other archaic humans. For tens of thousands of years, the question lingered. We had the modern body, but did we have the modern mind? To find the answer, you must travel to the rugged coastline of South Africa, to the mouth of a cave overlooking the shimmering Indian Ocean. This is Blombos Cave. The air is salty, the sound of the crashing surf is a constant roar, and the environment is rich with shellfish, fish, and edible plants. Around 100,000 years ago, a group of people who were physically identical to you made this cave their home. Imagine yourself inside, the light from the entrance illuminating the sandy floor. An archaeologist is kneeling, painstakingly brushing away the sediment from a small, fragile object. It is a flat, palm-sized piece of a reddish-brown, chalky stone. It's a piece of ochre. Ochre, a simple clay rich in iron oxide, is arguably the most important symbolic material in human history. This humble pigment is a thread that runs through hundreds of thousands of years of our story. Our ancestors used it for everything. Ground into a powder and mixed with fat, it could be a sunscreen or an insect repellent. Used as a preservative, it could help tan hides. And, most importantly, as a vibrant blood-red pigment, it was the primary color in the artistic and ritual palette of early humanity. But this particular piece of ochre from Blombos is different. It wasn't just used to make paint. It was the canvas itself. As the archaeologist's brush clears the last of the dust, you can see it clearly. The surface has been scraped and ground to create a smooth, flat facet. And on that facet, someone has carefully and deliberately engraved a pattern. It is a set of parallel lines, bisected by 3 other lines, and then crossed again by another set, creating a repeating cross-hatched, geometric design. This is not an accident. These are not the random scratchings of a bored individual. This is a deliberate, structured, abstract design. It is a symbol. This small red rock is one of the most important objects ever found for understanding the origin of the human mind. Why? Because it is, in a very real sense, a fossilized thought. It is the material proxy for language. The cognitive leap required to decide that this abstract pattern of scratches will represent an idea, whether it means this is my clan, or this is our property, or something we can never hope to translate, is the exact same cognitive leap required to decide that an arbitrary combination of sounds will represent an object or an action. The ability to make a mark mean something is the same mental hardware you need to make a sound mean something. This engraved ochre is hard evidence for a mind that can think symbolically. It demonstrates the ability to hold a complex, abstract concept in the brain, and then, critically, to externalize it, to reproduce it on an external medium for others to see and understand. This discovery shattered old timelines that placed the dawn of art and symbolism much later in Europe. But it also opened up a new debate. Did these engravings represent the true dawn of a continuous symbolic tradition? Or were they just a brief, brilliant flash, a flickering of modern consciousness that appeared and disappeared a few times before it finally caught fire for good? Scholars still argue whether this was the beginning of a steady burn or just a spark in the dark. But as you look at that small piece of ochre, it feels like a turning point. It's one of the first unambiguous messages sent to us from our distant past. A clear signal that the people living in this cave were not just modern in body, but were well on their way to becoming modern in mind. They were beginning to build a new kind of world, one that was saturated not just with things, but with meaning. That small engraved piece of ochre was a message in a bottle, a sign that the minds of our African ancestors were beginning to operate on a new symbolic level. But it was an isolated message, an abstract design. To truly understand the power of this new way of thinking, we need to see it become personal. We need to see it leap from a rock onto the human body itself. And for that evidence, we remain in the same time and place, in the coastal caves and rock shelters of southern Africa, around 100,000 years ago. Here, archaeologists have found another, even more intimate clue to the dawning of the modern mind. They found the world's first jewelry. The artifacts themselves are tiny and unassuming. They are the shells of a small sea snail called Nassarius. At first glance, a handful of these shells might not seem like much. But as you look closer, you realize this is no random beachcomber's collection. First, many of these shells are found in sites dozens, sometimes even hundreds, of miles inland, meaning they were deliberately transported far from their coastal home. Second, they have all been carefully selected for a similar size and shape. And third, and most importantly, each and every shell has a small, perfect hole punched through its lip, always in the same location. This is where the scientific detective work gets truly fascinating. Using powerful microscopes, archaeologists have meticulously examined these tiny perforations. They are not the work of a predator bird, nor are they the result of random erosion from being tumbled in the sand. The microscopic fracture patterns around the holes show they were deliberately and skillfully punched through with a sharp, pointed stone tool. Even more compelling is the evidence of use wear. The inside edge of these tiny holes is often smoothed and polished, with microscopic striations that are the telltale signature of friction. It's the kind of polish that can only be created by a string or a piece of sinew rubbing against the shell's sharp edge for a very, very long time. The conclusion is inescapable. These were beads, and they were meant to be worn. Why would someone 100,000 years ago go to so much trouble, collecting, transporting, and painstakingly perforating dozens of tiny shells? The answer is that these are not mere decorations. This is language made visible. This is a symbol system worn on the body. Each bead is a word, and the string of beads is a sentence. And that sentence broadcasts a wealth of social information to anyone who sees it. It might say, "I belong to the people of the coast." It could signify your status within the group. "I am an adult." "I am a skilled hunter." "I am married." In a world of expanding social networks, where you might encounter strangers for the first time, these beads would have been an instant social identifier, a visual resume that declared who you were and where you fit in. This is a profound cognitive step. It's one thing to make a tool that has a physical function. It's another thing entirely to make an object whose only function is to mean something. It's the birth of material culture. Anthropologists debate the precise meaning of these beads. Were they a simple marker of clan identity? Or were they part of a more complex system of reciprocal exchange, a kind of Stone Age currency that helped lubricate social and economic relationships between different groups? The fact that these specific shell beads have been found at sites across Africa and even into the Middle East suggests they were part of a vast, continent-spanning social network, a web of connections held together by a shared understanding of the value and meaning of these humble shells. You can think of this as a way of hacking our own neurology. The human brain has entire regions, like the fusiform gyrus, that are exquisitely specialized for recognizing and interpreting human faces and appearances. We are hardwired to scrutinize each other for social cues. Personal adornment, beads, body paint, tattoos, hairstyles, is a way of hijacking that powerful neural hardware and uploading more data onto our physical selves. It's an external hard drive for our identity. The mind that is capable of agreeing that a shell on a string means friend is the very same mind that is capable of agreeing that a specific sequence of sounds means water. The external world of symbols and the internal world of language are two sides of the same cognitive coin. This explosion of external symbolism is the clearest sign yet that the internal world of our ancestors was now governed by a new and powerful force: language. The beads on a string and the scratches on the ochre are the external proof. They are the artifacts of a mind that has begun to build a world of symbols. But this raises a profound chicken and egg question. We have been assuming that language evolved first and foremost as a tool for communication, a way to transmit thoughts from my mind to yours. But what if that's getting the story backwards? What if the primary and most powerful function of language didn't evolve for talking to others, but for talking to yourself? Pause for a moment and listen. Not to the sound of my voice, but to the voice inside your own head. The one that's currently processing these words, maybe adding a bit of commentary, perhaps wondering what's for breakfast tomorrow. That is your inner speech, the constant narrative stream that, for most of us, is the experience of conscious thought. It's so fundamental to our existence that it's hard to imagine a mind without it. This leads to an intriguing and powerful hypothesis. Language's first great evolutionary hurdle wasn't externalization, but internalization. Its first job was to organize the chaotic world inside the skull. Cognitive scientists have long debated this very problem. Did we develop language to express our pre-existing complex thoughts? Or did the structure of language enable complex thought in the first place? Let's explore the second idea. Imagine the mind of a pre-linguistic human. It would be a rich and vibrant place, a constant flood of sensory inputs, emotions, memories, and primal urges. But it might also be a blooming, buzzing confusion, a world of immediate experience without the tools to structure it, to hold it still for analysis. Now introduce the first great innovation of language, the mental label. The invention of a word, a stable sound concept like lion, allows you to reach into that chaotic stream of perception and pull out a single discrete idea. You have isolated it. You have categorized it. You have given it a handle. Once you have these mental handles for the important things in your world, lion, river, spear, fear, us, you can start to arrange them on your mental workbench. The next innovation, grammar, gives you the rules for how to connect them. Syntax is the engine that allows you to move beyond simple labels and build complex propositions. You can now construct a thought like, "The lion is by the river." This is a huge leap, but the truly revolutionary step is when you can add clauses and conditions. If the lion is by the river tomorrow, then we must take our spears and go over the hill. This is the birth of strategy. It is the ability to run simulations of the future inside your own head, to plan, to weigh options, and to learn from imagined mistakes without having to make them in the real world. An individual who developed this internal language of thought would have a staggering survival advantage, even if they never spoke a single word of it aloud. They would be a better planner, a more effective forager, a more cunning survivor. In this view, language evolved first as an internal cognitive tool, a new kind of mental software for organizing reality. Modern neuroscience lends powerful support to this idea. When you are lying perfectly still in a brain scanner and are asked to simply think in sentences, the very same language centers of your brain, Broca's area for structure, Wernicke's area for meaning, light up with activity. Your brain is running its language engine, composing and comprehending, all without making a single sound. And even more strangely, when you think or read silently, sensitive instruments can often detect tiny, involuntary muscle movements in your vocal cords and tongue, a phenomenon called sub-vocalization. Your body is physically tracing the outlines of the silent words in your head, showing how deeply the internal and external systems are connected. The public, spoken language we use every day would have been the second, and perhaps easier step in this process. Once this incredibly powerful internal operating system was up and running, the pressure to externalize it, to link your structured thoughts to the thoughts of others, would have been immense. Sharing your plans and models of the world with your group would amplify their power 1,000-fold, creating a collective intelligence, a shared consciousness. The revolution began inside one mind, but it was about to take over the world. This new powerful internal language, this private software for organizing reality, was a revolution waiting to happen. The final step was to connect individual minds, to create a network. So when did our species flick the switch? When did we externalize this inner world and become the fully symbolic, chattering, art-making beings we are today? For many years, the most popular answer to this question was a simple and dramatic story. It was called the Human Revolution, or the Great Leap Forward. The theory was born from the archaeological record of Europe. Around 45,000 years ago, our species, Homo sapiens, arrived on that continent, which had long been the domain of the Neanderthals. And in the layers of dirt and rock, it looked like a revolution had indeed occurred. Almost overnight, the archaeological record seemed to explode with a new kind of creativity. The static, slow-changing toolkits of the Neanderthals were replaced by a dynamic array of sophisticated new technologies. Long, elegant blade tools, finely crafted spear throwers, and for the first time, bone needles, hinting at tailored clothing. But even more spectacularly, this was the moment that art appeared in all its glory. You see the magnificent galloping horses and bison painted on the walls of Chauvet and Lascaux caves. You see the strange, stylized Venus figurines carved from mammoth ivory. You even see the first musical instruments, elegant flutes carved from bird bone. Faced with this sudden, dazzling fluorescence of culture, the explanation seemed obvious. Something dramatic must have happened. The theory proposed that a single, lucky genetic mutation occurred in an African population of Homo sapiens around 50,000 years ago. This mutation, it was argued, rewired the brain, instantly creating the capacity for full, syntactic language and the symbolic thought that goes with it. Armed with this new cognitive superpower, this group of humans swept out of Africa, and their superior communication and cooperation skills allowed them to outcompete and replace all other archaic humans around the world, including the Neanderthals. It was a clean, simple, and dramatic story, and it has now been almost completely dismantled by the evidence. The Great Leap Forward was a Eurocentric illusion, born from a time when the archaeological record of Africa was poorly understood. The key to debunking the myth was lying in the sand of caves like Blombos. Remember that engraved piece of ochre? It dates to 100,000 years ago, a full 50,000 years before the supposed revolution. And it wasn't an isolated find. At other South African sites like Diepkloof Rock Shelter, archaeologists have found fragments of ostrich eggshells used as water canteens that were engraved with geometric patterns 60,000 years ago. The shell beads you saw earlier are older still. This is the hard evidence that symbolic thought, art, design, personal identity was not born in a sudden flash at 50,000 years ago. It has a much deeper, older, and exclusively African history. So if it wasn't a great leap, what was it? A much better metaphor is the slow fuse. Imagine a firework that takes 300,000 years to go off. The components of modern human behavior were not created in a single instant. They were assembled, piece by piece, over a vast stretch of time. The anatomical hardware for the voice was in place 500,000 years ago. The genetic toolkit, like FOXP2, was present in our common ancestor with Neanderthals. The cognitive foundations of an internal language of thought were being laid. The symbolic sparks we see at Blombos were not the start of the fire. They were just visible signs that the fuse was burning. The spectacular explosion of culture seen later in Europe wasn't the lighting of this fuse. It was the moment the fuse finally reached the powder keg. But what was the keg? It may not have been a change in our brains at all, but a change in our societies. This is the social density hypothesis. For much of our history, human populations were small and fragmented. Innovations could easily be lost, a brilliant idea dying with the small band that invented it. But at a certain point, perhaps due to favorable climate changes in Africa, populations grew larger and became more interconnected. When you reach a critical mass of networked minds, ideas can be shared, combined, and improved upon faster than they are forgotten. Culture suddenly becomes cumulative. It can build on itself, generation after generation, creating a runaway feedback loop of innovation. The debate among archaeologists is no longer about if this process was gradual, but about what forces, social, environmental, or demographic, drove this slow burn to its spectacular conclusion. We are not the children of a single miraculous leap. We are the result of a long, slow, patient assembly. And the final, most intricate component to be installed was the engine of infinite creativity, grammar. The fuse burned slowly, and the cultural powder keg finally ignited. We now have a new model for our origins, a gradual, piecemeal assembly of the modern human mind and its symbolic capabilities. But this leaves us with the most difficult question of all. Where did grammar come from? We have the words, the mental labels like lion and spear. We have the desire to communicate. But how did we discover the magic of syntax? How did we learn to string those words together into complex, rule-governed sentences that can convey intricate meaning? How did lion, spear, run become we must run because the lion that we saw earlier has returned without its spear wound? This is one of the deepest and most contentious debates in all of cognitive science. A battle of ideas that has raged for over half a century. It boils down to a simple, fundamental question. Is grammar a biological instinct or a cultural technology? In one corner, we have the nativist camp, and its champion, the legendary and formidable linguist Noam Chomsky. In the mid-20th century, Chomsky started a revolution by proposing a radical idea. universal grammar. He argued that if you strip away the superficial differences in vocabulary and pronunciation, all 7,000 human languages are fundamentally the same. They are all built upon a shared, underlying scaffolding of abstract rules and principles. And this universal grammar, he claimed, is not something we learn. It is an innate part of our biological heritage, a kind of language organ that is hardwired into the human brain from birth. The primary evidence for this view is what Chomsky called the poverty of the stimulus. Watch a young child learn to talk. It's a miracle of effortless acquisition. They are not formally taught the complex rules of grammar, and the language they hear around them is often messy, full of errors and incomplete sentences. Yet, from this limited and imperfect input, they rapidly deduce the underlying system and begin to produce completely novel, grammatically perfect sentences they have never heard before. How is this possible? For Chomsky, the only explanation is that the child isn't starting from a blank slate. The basic blueprint for grammar is already there. The child's job is simply to figure out which specific settings and parameters their local language uses. In this view, the emergence of grammar in our species may have been a sudden biological event, the result of a single powerful mutation that rewired the brain to handle recursion, the trick of embedding thoughts within thoughts. In the other corner is the cultural evolution camp. They look at the same phenomenon and come to a completely different conclusion. Grammar, they argue, is not a biological instinct. It's a cultural technology. It is a brilliant tool that we, as a species, collectively invented to solve the problem of communicating complex ideas more efficiently. It's no more a part of our biology than the alphabet or the internet. It's a piece of software we designed for our pre-existing biological hardware. According to this view, grammar was not born in a flash. It was built slowly, over thousands of generations. It began with the simple two-word proto-language of our ancestors. Throw spear. Over time, through the messy everyday process of people trying to make themselves understood, new conventions would have emerged. A certain word order becomes standard because it's less ambiguous. New words arise to mark tense or possession. These small improvements, if found useful, are copied and passed down to the next generation of learners, who might then refine them further. Grammar, in this model, is like a well-worn path through a forest. It is the cumulative result of countless journeys, a shared solution that has been optimized over time. For a long time, this was a difficult theory to prove. But then, a stunning real-world experiment unfolded in the 1980s. In Nicaragua, a new school for the deaf was opened, bringing together deaf children from isolated villages who had no shared language. The first students created a simple system of home signs to communicate. But then, something amazing happened. The younger children who entered the school took this raw, unstructured sign system, and within a single generation, spontaneously imposed a complex and consistent grammar upon it. They invented rules for word order, for tense, for motion, creating a new, fully fledged language right before the researchers' eyes. This was Nicaraguan Sign Language, and it was a powerful demonstration of grammar being born not from an innate blueprint, but from the social need to communicate. The debate today is far from settled, and many modern linguists believe the truth lies somewhere in the middle. Perhaps our brains do come with an innate biological predisposition to learn patterns and structures, a language-ready state. But the specific rules, the intricate nuts and bolts of the grammar you speak, are a product of the cultural history of your people. It is a dance between nature and nurture, between a biological instinct and a cultural invention that finally put the engine of syntax at the center of the human mind. Let's assume the truth lies in that fertile middle ground, that our brains were biologically primed for language, but the intricate and beautiful structure of grammar was a cultural construction. If that's the case, then grammar wasn't handed down from on high by a miraculous mutation. It was built, brick by brick, by ordinary people trying to solve the practical problems of their daily lives. So where were the workshops? What were the social pressure cookers that forced us to invent the rules that transformed simple words into a tool of infinite power? To find out, let's return to that community in southern Africa, 80,000 years ago. You are watching a master flint knapper trying to teach a teenager the delicate art of making a fine stone point. The survival of your group depends on the effective transmission of this kind of complex skill. Let's listen to the evolution of the instruction. The teacher starts with proto-language. Hit stone. The apprentice takes a hammerstone and smacks the wrong part of the core, sending a useless flake flying. The teacher shakes his head. No, hit here. He points. This is better, but it's slow and inefficient. Now imagine a slightly more advanced system. The teacher can specify, hold the big stone, strike the small stone. This is clearer, but what if there are several big stones and several small stones? Language needs to become more precise. It needs adjectives. Hold the flat big stone. Better. But the real breakthrough comes with the invention of grammar that can handle complexity and reference. The teacher needs to correct a mistake while referring to a specific object with a history. He needs recursion. Hold the stone, he might say, and then pause, seeing the apprentice reach for the wrong one. No, not that one. Hold the stone that you found by the river yesterday. That embedded clause is a miracle of communication. It allows the teacher to precisely identify an object by referring to a shared past experience. Then he can finish the instruction and strike it just below the spot where the last flake came off. This level of detail, this ability to embed ideas and specify relationships, would have been a game changer for teaching complex skills. Groups that developed this kind of grammatical technology would have learned faster, made better tools, and ultimately outcompeted those who had not. Now let's move from the workshop to the creche. Another profound pressure cooker for grammar was the unique challenge of raising a human child. Our children are born incredibly helpless and have a uniquely long childhood. This requires a huge investment of care, often shared among many members of the group, a system known as allo-parenting, where aunts, grandparents, and siblings all help raise the young. This means that vital information about safety, food, and social rules needs to be transmitted with perfect fidelity between multiple caregivers and multiple children. Simple commands are not enough. A child doesn't just need to learn, "No eat red berries." They need to learn the complex conditional rule. You must not eat the red berries that grow on the bush with the shiny leaves, unless an adult has cooked them in the fire first, because they will make your stomach sick. This single vital instruction requires relative clauses, conditional clauses, unless, negation, and a way to talk about cause and effect. This is the grammar of survival, built to navigate a world of hidden dangers and complex social obligations. But how do these grammatical tools, the words for if, unless, because, and that, actually come into being? They are created through a beautiful and efficient process that linguists call grammaticalization. It's a form of linguistic reselling. Languages rarely invent new grammatical words from scratch. Instead, they take common, concrete words, usually nouns or verbs, and, over long periods of use, bleach them of their original meaning and repurpose them to serve a grammatical function. A perfect example is the future tense in English. We say, "I am going to eat." The word go started its life as a simple verb of motion. You would say, "I am going to the river." Then it was used to state purpose. "I am going to the river to hunt." Over time, the destination becomes less important than the intention. The phrase gets shortened. You can now say, "I am going to hunt," even if you aren't moving at all. The word go has lost its meaning of physical travel and has been grammaticalized into a marker for the future tense. The same thing happened with the word will, which originally meant to want or to desire. "I want to eat" slowly morphed into the future, "I will eat." Scholars still debate which social pressure was the primary forge for grammar. Was it the need for precise teaching? The demands of childcare? The desire for better storytelling? The truth is, it was likely a feedback loop of all of them. The need for clarity in one area of life would create a new grammatical tool, which would then be available to solve problems in another. Grammar wasn't designed by a committee. It grew, organically and unconsciously, from the soil of everyday human interaction. The grammar grew from the rich soil of social life, from the need to teach, to parent, and to cooperate. This slow cultural construction, built upon a ready biological foundation, finally produced the finished article. The engine was complete. Now let's see what it could do. We leave the sunny plains of Africa and travel north into the frigid, wind-swept landscape of Ice Age Europe, 40,000 years ago. You are standing on a ridge overlooking a vast, grassy steppe, watching a herd of woolly mammoths move like great, shaggy mountains in the distance. In the shelter of a limestone cliff, a fire burns, and around it are gathered a group of people. They are tall and slender, dressed in beautifully tailored furs, sewn together with fine bone needles. These are the Cro-Magnons, the first modern Homo sapiens to make Europe their home. And as you look at them, a stunning realization dawns. They are not like us. They are us. This is a critical turning point in our story. We are no longer talking about archaic, transitional humans. These people are fully, completely modern. Their skeletons are our skeletons. Their genes are our genes. Their brains, housed in high, rounded skulls, are indistinguishable from our own. If you were to transport one of their infants into our time and raise them, they would be a perfectly normal 21st century human, capable of learning calculus, composing a symphony, or flying a helicopter. The long, slow process of assembly is over. The hardware is finished, and this means that their capacity for language must have been identical to our own. So let's approach the fire, and in the flickering light, let's listen. What would the voice of the Ice Age have sounded like? The first thing you would notice is that the vocabulary, the actual words they are using, would be utterly and completely alien. You wouldn't recognize a single one. Language changes at a ferocious pace. Just think of how difficult it is to understand Chaucer's English from 600 years ago. Now multiply that distance in time by more than 60. After 40,000 years, not a single sound, not a single word would have survived in any recognizable form. To our ears, their speech would be a stream of beautiful but incomprehensible gibberish. But if you could listen past the unfamiliar words and focus on the structure, the music of their language, you would feel a sudden, shocking sense of familiarity. The underlying architecture would be instantly recognizable. You would hear that their speech was neatly segmented into nouns and verbs, adjectives and adverbs. You would discern a consistent word order, a syntax that governed how ideas were put together. You would hear them use tense, effortlessly shifting between a story about yesterday's hunt, the task at hand, and their plans for tomorrow. You would recognize the rising intonation of a question, the sharp finality of a command, the subtle rhythm of a narrative. And woven throughout it all would be the magic of recursion, the effortless embedding of thoughts within thoughts, allowing them to express complex, nuanced ideas. You wouldn't understand a single sentence, but you would know, with absolute certainty, that this is language. This is the voice of a people whose inner world is as complex as our own. To see the proof, you need only follow them when they take a flaming torch and venture deep into the earth, into the sacred darkness of a cave like Chauvet or Lascaux. There, on the walls, they leave behind the products of their symbolic minds. Breathtaking paintings of lions, horses, rhinos, and mammoths, so full of life they seem to move in the flickering light. Archaeologists and art historians have long debated the purpose of these magnificent paintings. Were they a form of hunting magic to ensure success? Were they the visions of shamans on a journey into the spirit world? Or were they a kind of library, a visual record of the clan's most important myths and stories? Some researchers have pointed to a fascinating clue: the acoustics of the caves. The paintings are often located in chambers with remarkable resonance. Stand where the great bulls are painted, and a clap or a chant will echo powerfully. This has led to the acoustic hypothesis, the idea that sound, story, and song were an integral part of the experience. Imagine it. The storyteller's voice, full of rhythm and melody, filling the resonant space, the torchlight making the painted beasts dance on the walls. It was a complete, multi-sensory immersion into the world of the imagination. This is what full, modern language allows. It is the tool that lets us build shared worlds inside our minds. The tool was finally forged. The next chapter of our story is not about its creation, but about its incredible, globe-spanning diversification. You are standing at the edge of the world. Not the whole world, but the world of our species, 70,000 years ago. For over 200,000 years, modern Homo sapiens have been confined to Africa. But now, something is happening. A small group of these fully modern, fully linguistic humans is making its way out of the continent, likely across the narrow strait at the southern end of the Red Sea. Geneticists and archaeologists still debate the exact size of this founding population. Was it a few hundred individuals or a few thousand? But the evidence is clear. This was the seed from which almost all non-African people on Earth today would grow. And as they traveled, they carried with them the most powerful tool ever invented: language. We can assume they spoke either a single language or a small cluster of closely related dialects. A mother tongue for all of humanity. This simple fact presents us with a beautiful paradox. If we all descend from this small population of founders, all speaking the same language, why is the world today not a linguistic paradise of perfect understanding? Why, instead, do we live in a great, chaotic Babel of over 7,000 distinct, mutually unintelligible languages? If the purpose of language is to connect us, why has it fractured so spectacularly into a tool of division and confusion? The answer lies in two powerful and relentless forces that began to act upon that mother tongue the moment our ancestors began their journey across the globe. The first and most fundamental force is geographic isolation, which gives rise to a process of linguistic drift. It works just like biological evolution. Imagine a single growing tribe. Eventually, it becomes too large to support itself in one place. A decision is made, and the group splits in two. One half stays in the familiar coastal territory. The other half, a small founding group, travels inland, over a mountain range, and into a new, empty river valley. For the first few years, they remain in contact. But as the generations pass, the journey over the mountains becomes too difficult, and contact ceases. The two groups are now isolated. Now, just wait. Language is never static. It is a living, fluid thing, constantly changing in small, almost imperceptible ways. In the Valley group, a charismatic leader might have a slight lisp, and over time, that subtle shift in the pronunciation of the S sound becomes the new normal for their children. A new, faster, more dangerous kind of wildcat appears in the valley, and a slang term invented by the hunters to describe it quickly becomes the standard word. Meanwhile, back at the coast, a different set of small changes is taking place. An old, complicated grammatical rule for possession starts to fall out of use because a simpler construction works just as well. These changes are random, unconscious, and directionless. They are the linguistic equivalent of genetic drift. And just as in genetics, the founder effect is powerful. The specific idiosyncratic speech patterns of the small band that first settled the valley will have an outsized influence on the entire future of the language that evolves there. After 500 years of this slow, steady, and separate drift, the changes begin to accumulate. After 1,000 years, if a trader from the coast were to make the journey over the mountains into the valley, he would be met with a strange and bewildering dialect. He might be able to pick out a few words here and there, but the accent would be thick, the vocabulary strange, the grammar unfamiliar. After 2,000 years, the two languages would be completely unintelligible. Two distinct languages have been born, not through any conscious act of invention, but through the simple, inexorable mechanics of time and isolation. Now add the second great force, the construction of social identity. Language is not just a tool for sharing information, it is a badge. It is the primary, audible, and undeniable signal of who you are, of which group you belong to. It is the ultimate marker of us versus them. Imagine our two groups in the valley and on the coast are no longer isolated. They are now competitors, their territories bordering each other. Now, the subtle differences in their speech are no longer just quirks. They become potent symbols of identity. The valley people might begin to take a stubborn pride in their way of speaking, unconsciously exaggerating the very features that distinguish them from the arrogant coastal people. The coastal peoples, in turn, might mock the lazy, slurred speech of the valley dwellers. This active social pressure, this desire to be different, acts like an accelerator on the process of linguistic drift, driving the two languages further and further apart. These two forces, the passive drift of isolation and the active push of identity, are the twin engines of linguistic diversification. As that small band of founders spread out from Africa into the vast, empty landscapes of Asia, Europe, and the Americas, this process was repeated 1,000 times over. Groups split, migrated, and became isolated. Over tens of thousands of years, that single mother tongue was fractured, splintered, and reshaped by time, geography, and the human need to belong, creating the magnificent and bewildering tapestry of voices we hear across the world today. The result of these relentless forces of isolation and identity is the world we have today, a beautiful but bewildering linguistic chaos. It seems as if the Tower of Babel did indeed fall, shattering a single clear language into thousands of incomprehensible fragments. But what if we could reverse the process? What if we could gather up those fragments, examine their broken edges, and piece them back together to reconstruct the original? Is it possible to find the echo of that single mother tongue? The answer is yes, and the science that attempts this incredible feat is historical linguistics. Its guiding principle is a powerful analogy. Words behave like genes. Like genes, words are passed down from one generation to the next. And like genes, they mutate. Pronunciations shift, meanings drift, and new words are created. By tracing these mutations backward in time, linguists can group languages into families, just as biologists group species into genera and phyla. You might be surprised to learn, for instance, that the English you are hearing right now is a close cousin to German and Dutch, a more distant cousin to Russian, Spanish, and Irish, and a very distant, but still related, cousin to Persian and Hindi. All these languages, and hundreds more, belong to a single vast clan known as the Indo-European family. They are all the modern descendants of a single language, a proto-language, spoken by a group of people thousands of years ago. The discovery of this hidden family connection is a fascinating story in itself. In the 1780s, a brilliant British judge and scholar named Sir William Jones was working in India. He began studying Sanskrit, the ancient classical language of the subcontinent. As he did, he was struck by an uncanny and profound similarity between its vocabulary and grammar, and those of the classical languages he already knew, Latin and Greek. The resemblances were too numerous and too systematic to be a coincidence. He famously concluded that all three must have sprung from some common source, which perhaps no longer exists. He had uncovered the ghost of Proto-Indo-European. But a ghost of an idea is not proof. The proof came from a rigorous technique developed in the 19th century, known as the comparative method. This is the scientific engine of historical linguistics. The method is not about finding a few random words that sound similar. Those can often be borrowings or pure coincidence. Instead, it's about identifying systematic, regular sound correspondences in the core vocabulary of languages. Core vocabulary consists of words for universal concepts that are resistant to being borrowed from other languages. Pronouns: I, you, we, body parts, hand, foot, I, numbers, 1, 2, 3, and basic elements of the natural world: water, sun, star. Let's take a simple example. The English word for the number 3 starts with a th sound. In German, it's dre, de. In Latin, it's tres, ter. In Welsh, it's tri, t. And in Russian, it's tri, te. A historical linguist sees this pattern and can establish a regular correspondence. Where English has th at the beginning of a word, many of its cousins have a t sound. By identifying hundreds of these non-random, predictable sound shifts, they can essentially create a set of rules for translating back in time. They can reverse the mutations step by step and reconstruct the original proto-word that gave rise to all of them. In this case, something like trays. By doing this for hundreds of words, they can build up a detailed portrait of the lost proto-language. This ability to build language family trees is powerful, but it leads to another question. Can we put dates on the branches? A controversial but fascinating attempt to do just that is a method called glottochronology. Pioneered by the linguist Morris Swadesh in the 1950s, the idea was to create a linguistic word clock. Swadesh compiled a list of about 100 core vocabulary items he believed were universal to all cultures. He then proposed that any language will replace words on this list at a roughly constant rate, about 14% every 1,000 years. In theory, you could compare the Swadesh lists of two related languages, count how many core words they still share, and calculate how many centuries have passed since they split apart. This idea, however, is highly controversial among linguists today. The central problem is that the rate of change is not, in fact, constant. Language change can be sped up by intense social contact, or slowed down by cultural conservatism. The word clock is unreliable. Yet the dream it represents, of having a molecular clock for culture, is a tantalizing one. It reminds us that historical linguistics is a form of archaeology. Its practitioners are not digging in the dirt for pots and bones, but in the sounds and structures of modern languages, searching for the fossilized remains of the lost worlds and forgotten voices of our deep past. That science of linguistic archaeology can seem abstract and complicated. So let's make it concrete. Let's put on our gloves, pick up our tools, and excavate the history of a single, familiar word. We're going to perform a live demonstration of the comparative method, digging down through the layers of time to find the ancient, fossilized root of a word you use every day, the word mother. We begin at the surface, with the modern English word itself, mother. The eth sound in the middle is our starting point. Our first step is to dig down to the layer immediately below. Old English, the language of the Anglo-Saxons, spoken a little over 1,000 years ago. There the word was modor. The family resemblance is obvious. We can see a slight mutation. The D sound in modor has, over the centuries, shifted to become the eth sound in our modern mother. Next, let's look at a sibling language in our immediate family, the Germanic branch. In modern German, the word is Mutter. Again, it's clearly the same word, just with a slightly different accent. Based on these and other Germanic relatives like Dutch moeder and Swedish mor, linguists can confidently reconstruct the common ancestor of all of them, the Proto-Germanic word, which was something very close to moder. That little asterisk, by the way, is a convention linguists use to show that a word is a reconstruction, not a written record. Now the real magic begins. We are going to jump to a completely different branch of the Indo-European family tree. Let's travel to ancient Rome and look at Latin. In Latin, the word was mater. Notice the key difference. Where the Germanic words had a D sound, Latin has a T. Let's jump again, this time to ancient Greece. The word was meter. There it is again. The T sound. Let's make one final, enormous leap, all the way to ancient India and the classical language of Sanskrit. The word was mata. Once more, that telltale T sound. Now let's lay our evidence out on the table. We have Old English moder, German mutter, Latin mater, Greek meter, and Sanskrit mater. Seeing them side by side, the idea of coincidence becomes ludicrous. These are not borrowings. This is a clear genetic signature, a set of mutations inherited from a common ancestor. By applying the systematic sound laws they have discovered, linguists can now reverse the changes. They know that the D in Germanic regularly corresponds to a T in Latin, Greek, and Sanskrit. So they can confidently reconstruct the original sound as a tier. Working this way through all the sounds in the word, they can resurrect the ancestral form. They can hear the ghost. The reconstructed word for mother in Proto-Indo-European, the language spoken some 5,000 to 6,000 years ago, was me etuter. This word has never been written down. The people who spoke it were pre-literate. Its existence is a pure scientific inference, but it's an incredibly robust one. And here's a fascinating quirk. While this specific reconstruction is for the Indo-European family, words for mother that are based on an M sound and words for father based on a P or B sound appear in thousands of unrelated languages all over the world. This has led to the mama-papa theory. The idea is that these are not shared because of a deep linguistic ancestry, but because of universal human biology. The M, P, and B sounds are bilabial. They are made by simply putting the lips together. They are among the very first and easiest sounds a human infant can make. The theory goes that a baby's first babbling sounds of mama ma get interpreted by the primary caregiver as being addressed to her. And the name sticks. In a very real sense, we may not have named our mothers. They might be named for the first sound we ever made. This single reconstructed word, me etuter, is a time capsule. It connects you, right now, to a woman living on the vast grassy steppes of Eurasia more than 5 millennia ago. Scholars still passionately debate where exactly this language was spoken. The current frontrunner is the Kurgan hypothesis, which places the homeland in what is now Ukraine and southern Russia. But the language itself tells us about the people. They had words for wheels, horses, wagons, and wool. They were a pastoralist people, on the move. Every time you say the word mother, you are unknowingly echoing her voice. It is a fossil made of sound, a direct, unbroken thread of inheritance that stretches all the way back into the deep past. That single reconstructed word, mechtuter, is a testament to the power of historical linguistics to find order in the chaos, to see the family trees hidden within the great forest of human languages. But for the last 10,000 years, a new and powerful force has been at work, not creating diversity, but culling it. It was a revolution that began not with a word, but with a seed. Let's travel to the rolling hills of the Fertile Crescent in the Middle East, around 10,000 years ago. The last ice age has ended, and the climate is growing warmer and more stable. You are watching a small group of people engaged in a strange new activity. They aren't just gathering the wild grasses that grow on the hillsides. They are actively cultivating them, saving the seeds from the most plump and promising stalks and planting them in prepared ground. They are domesticating wheat and barley. Nearby, another group is managing a herd of wild goats, selectively breeding the most docile animals. This is the dawn of the Neolithic Revolution. This is the invention of farming. It's impossible to overstate the consequences of this innovation. For millions of years, our ancestors had been nomadic hunter-gatherers, living in small, mobile bands, their population size strictly limited by the wild resources around them. Farming changed everything. For the first time, it allowed for a reliable food surplus. A food surplus meant you could support a much larger population in a much smaller area. Small, mobile bands were replaced by large, settled villages. And these villages began to grow. This demographic shift, the population explosion of the first farmers, would have a catastrophic and permanent effect on the linguistic landscape of our planet. This is the central idea behind the farming language dispersal hypothesis. As the populations of these first agricultural communities swelled, they needed more land to plant their crops and graze their animals. So they began to expand. It wasn't an invasion or a conquest in the modern sense, but a slow, relentless, generational creep. Every year, a few families would move into the next valley to start a new farm. And as these farmers moved, they took their tools, their seeds, their animals, and their language with them. In every new valley, they would have encountered the indigenous hunter-gatherer peoples who had lived there for tens of thousands of years. These foraging populations were sparse, living at a much lower density, and their world was likely a rich patchwork of incredible linguistic diversity, with every small band speaking its own distinct language. Now, what happened when the slow, unstoppable wave of farmers met this ancient, diverse world? Scholars debate the exact nature of this spread. Was it a wave of farmers completely replacing the local foragers through violence and disease? Or was it a slower process of cultural diffusion, where the foragers were gradually absorbed, adopting the farmers' lifestyle and, with it, their language, because it was the language of power and economic success? Whatever the precise mechanism, the linguistic result was the same: extinction. The handful of farming languages expanded, while the thousands of hunter-gatherer languages vanished. We can see this pattern in two of the most dramatic case studies on Earth. The first is the spread of the Indo-European languages we've already discussed. One of the leading theories for their expansion is that the original speakers were among the world's early agriculturalists or pastoralists. As they and their descendants spread across Europe, their language replaced the dozens, perhaps hundreds, of ancient, unrelated Paleolithic languages that were spoken there before them. The Basque language, spoken in the Pyrenees Mountains, is thought to be the last lonely survivor of that pre-Indo-European world. The second great example took place in Africa. Around 5,000 years ago, a group of farmers speaking languages belonging to the Bantu family began to expand from their homeland in west-central Africa. Armed with iron tools and a robust agricultural package, they spread south and east across the continent. Before them lay a world inhabited by diverse groups of hunter-gatherers, like the ancestors of the modern Khoisan and Pygmy peoples. Today, almost all of sub-Saharan Africa speaks a Bantu language. The ancient hunter-gatherer languages, with their incredible phonetic complexity, including the famous click consonants, now survive only in a few pockets of southern and central Africa. This suggests a fascinating and melancholy possibility. The spread of farming may have actively simplified the soundscape of human language, wiping out unique and complex phonetic systems across the world. The invention that gave us cities, empires, and civilization was also the single greatest extinction event in the history of human language. It was a great flood that washed away a world of ancient voices, leaving only a few sprawling superfamilies in its wake. Thousands of unique ways of seeing the world, thousands of stories, thousands of words for which we will never know the meaning, were silenced forever. That great agricultural flood was a destructive force, wiping out a world of linguistic diversity. But the very process that caused this extinction, the expansion of a single language family over a vast territory, provides modern science with an incredible tool. It creates a trail of cultural DNA that we can follow. By tracking the spread of a language family, we can reconstruct some of the most epic and forgotten chapters of the human story. And there is no greater example of this than the story of the most widespread language family on Earth, the Austronesian expansion. It is a story of one of the most remarkable feats of exploration in human history, a journey that makes the voyages of the Vikings or Columbus seem like a trip across a pond. Our story begins on the island of Taiwan, about 5,000 years ago. The people living on the coasts were skilled farmers and fishers, but they were also master boat builders and navigators. They had developed a revolutionary piece of maritime technology, the outrigger canoe. This stable, swift vessel was their key to unlocking the largest, most intimidating frontier on the planet, the Pacific Ocean. For reasons we still don't fully understand, they began to sail south. They crossed the strait into the Philippines. From there, they began to spread, island by island, across the vast archipelago of Indonesia. Their journey then split. One wave of migration pushed east out into the open Pacific, settling the thousands of islands of Melanesia, Micronesia, and finally, the remote corners of the Polynesian Triangle. Hawaii to the north, New Zealand to the south, and the impossibly isolated Easter Island to the east. In another, almost unbelievable feat of seamanship, a different wave of these sailors pushed west, out of the Indonesian islands, across the entire unbroken expanse of the Indian Ocean, to settle the island of Madagascar, just off the coast of Africa. In the space of a few thousand years, a small group of Taiwanese islanders had populated a territory stretching more than halfway around the globe. How can we possibly know this incredible story is true? The first and most powerful line of evidence was not found by archaeologists digging in the sand, but by linguists listening to the people. They noticed something astonishing. The native languages spoken in Madagascar, the Philippines, Malaysia, Indonesia, New Zealand, and Hawaii were all profoundly related. Despite being separated by thousands of miles of ocean, Malagasy, Tagalog, Malay, Maori, and Hawaiian are all sibling languages. They all belong to one great Austronesian family. This linguistic fingerprint not only connects these disparate peoples, it also allows us to pinpoint their origin. To do this, linguists use a simple but powerful principle. The center of diversity is the center of origin. Think of it like this. If you were searching for the original homeland of the apple, you wouldn't go to a place that has just one type of apple tree. You would go to the region where you find the most ancient, diverse, and genetically distinct varieties of apples growing in the wild. That is its homeland. The same is true for language. The homeland of a language family is the place where you find its oldest and most divergent branches. While the vast majority of Austronesian languages are spoken in the Philippines and Indonesia, these languages are all quite similar to each other, belonging to just one branch of the family tree. But on the small island of Taiwan, a tiny number of indigenous people still speak a dozen different Austronesian languages that are radically different from each other and from all the others. Taiwan contains almost all the primary branches of the Austronesian family tree. It is the linguistic Garden of Eden, the smoking gun that proves beyond any doubt that this incredible migration began from there. Later, other sciences came in and confirmed the story told by the words. Archaeologists discovered a distinctive style of pottery, known as lapita pottery, that follows the exact path of the linguistic expansion out into the Pacific. Geneticists then analyzed the DNA of the people, their domestic pigs, their chickens, and even the rats that stowed away on their canoes. The genetic trail tells the exact same story, a direct line of descent leading all the way back to the indigenous people of Taiwan. Of course, the story was not always simple. Archaeologists and linguists still debate the complex interactions between the incoming Austronesian sailors and the Papuan peoples of New Guinea, who had already lived there for tens of thousands of years. It was a story of mixing, trading, and conflict, not just a simple replacement. Still, the Austronesian expansion is the ultimate proof of concept. It shows how language can act as a fossil, preserving the memory of our ancestors' journeys in its grammar and vocabulary. The words we speak are not just arbitrary sounds. They are maps. They are the logbooks of 1,000 forgotten voyages, a living record of the restless, exploratory spirit that carried our species to every corner of the earth. The words of our ancestors have, up to this point, been ephemeral things. They were living, breathing sounds that danced in the air for a moment and then vanished forever. For 99% of its long history, human language was a creature of memory alone. A story, a law, or a piece of history was only as permanent as the chain of human minds willing to remember it and pass it down. Knowledge was a captive of breath and brain. But then, in the grand scheme of our story, just a moment ago, around 5,000 years ago, a second great revolution occurred. We found a way to trap our words, to give them weight and permanence. We invented writing. The revolution began not in a quiet scholar's study, but in the noisy, bustling heart of the world's first great cities. Let's travel to the city of Uruk in Mesopotamia, in what is now modern-day Iraq, around 3200 BCE. This is a thriving metropolis of tens of thousands of people. Great temples rise to the sky, and vast storehouses bulge with grain, beer, and textiles. A complex economy of trade and taxation is taking shape. And this new urban complexity created a brand new problem: information overload. The human memory, which had served our species so well for 100,000 years, was no longer a reliable enough hard drive. How do you keep track of who has paid their taxes to the temple, or how many sheep are in the city's herds? The solution was not invented by a poet trying to immortalize a verse, or a king wanting to boast of his victories. The first writers were accountants. The first written documents were spreadsheets. You can picture the scene: a temple scribe, a bureaucrat, holding a small, damp tablet of clay. With a sharpened reed stylus, he carefully presses wedge-shaped marks into its surface. A stylized picture of a head of barley, next to a series of marks indicating the number 3. He is not writing a story. He is writing 3 bushels of barley. This is the humble and perhaps slightly boring birth of the written word. From these simple pictorial beginnings, writing evolved through a series of brilliant cognitive leaps. The first stage was pictographic, where a simple drawing of a thing represents the thing itself. An image of a bull means bull. This is intuitive, but you can't draw a picture of love or because. The next step was logographic, where the symbol came to represent not the object, but the spoken word for the object. The stylized wedge marks for a bull now meant the Sumerian word gu. This was a crucial link between the visual sign and the linguistic system. The true breakthrough, however, was the discovery of the rebus principle. This was the moment writers realized a symbol could represent a sound, completely detached from its original meaning. In English, you could write the abstract word I by simply drawing a picture of an eye. You could express the word belief by drawing a bee and a leaf. This trick allowed scribes to write down any word they could speak, not just the ones they could draw. From this principle, true writing systems evolved. Some, like Japanese kana, became syllabaries, with a symbol for every syllable. The final and most efficient step was the alphabet, where each symbol represents a single individual sound, a phoneme. This reduces the entire system to just a couple dozen signs. A technology so powerful, it would conquer much of the world. This invention wasn't a one-off event. Writing was independently created at least 4 times in human history, in Mesopotamia, Egypt, China, and Mesoamerica. Scholars still debate whether the Egyptian system of hieroglyphs was inspired by the Mesopotamian one or was a completely independent invention. But its appearance at roughly the same time shows that complex societies everywhere were facing the same information management problems. The impact of this new technology was total. It transformed societies, allowing for the creation of fixed legal codes, like the Code of Hammurabi. It allowed for the recording of history, the administration of vast empires, and the accumulation of knowledge on a scale never before imagined. But it also transformed the human brain itself. We are not born to read. There is no reading circuit that evolved in our brains. So what happens when a child learns to read? Brain imaging studies provide the answer. A specific region of the brain's visual cortex, known as the visual word form area, or more charmingly, the brain's letterbox, gets repurposed. This small patch of neurons, which may have originally been for recognizing things like the edges of objects, painstakingly learns to recognize letters and strings of letters with lightning speed, acting as a physical interface between your eyes and the language centers of your brain. Learning to read literally rewires your neural hardware. It's a perfect example of a cultural invention reaching back and physically reshaping our biology. Writing unchained language from the limitations of memory and the fleetingness of sound. It gave our thoughts the power to cross deserts, oceans, and most miraculously of all, the vast abyss of time. The invention of writing gave our spoken words a kind of immortality, allowing a thought to echo through millennia. But whether our language is written in stone or whispered on the wind, it is built upon a single, profoundly elegant and deeply mysterious structural principle. The world around you is a place of near infinite complexity. There are millions of discernible shades of color, billions of individual objects, and a limitless number of possible actions and interactions. So why is your vocabulary so small? An average English-speaking adult has a vocabulary of around 20 to 35,000 words. It's an impressive number, but it is a pitifully tiny toolkit for describing an infinite universe. Why don't we have a unique word for everything? A specific word for the exact shade of blue in the evening sky, a different word for the way the light hits a wet leaf after it rains, another for the feeling of stepping on cold tile with a bare foot. The reason we don't is because of a fundamental constraint that has shaped language since its very beginning. Every language in every generation must pass through the narrowest of channels, the simplicity bottleneck of a child's mind. Language is not just a system for representing the world. It is a system that must be transmitted from one brain to another. A language with millions of unique, arbitrary words would be an impossible burden on memory. It would be unlearnable. No child could ever hope to master it, and so the language would die out in a single generation. Faced with this bottleneck, human language stumbled upon the same brilliant solution that biology did with DNA and that engineering did with Lego bricks. It discovered the explosive force of combinatorial power. Instead of creating an unwieldy, impossible-to-learn list with a unique word for everything, language uses an elegant two-tiered system. The first tier is a finite, learnable set of words, your lexicon. The second tier is a finite, learnable set of rules, your grammar, that tells you how to combine those words. And from the combination of that finite vocabulary and that finite set of rules, you can generate an infinite number of meaningful sentences. Think of it like a Lego set. You don't need a million different specialized bricks to build whatever you want. You need a reasonably small set of versatile bricks, the little squares, the long rectangles, the sloped pieces, and a simple, powerful system for snapping them together. That's your vocabulary. The simple rule that the studs on one brick fit into the holes on another is your grammar. With that small kit and that one simple rule, you can build a castle, a spaceship, a forest, or a city. You can build things the original designers never even dreamed of. This is the genius of human language. It is a system perfectly designed to be small enough to pass through the bottleneck of a child's mind, yet powerful enough to build and describe an entire universe of thought. You can even see this drive for efficiency in the statistical structure of language. If you take any large body of text, a novel, a collection of newspapers, a transcript of conversations, and count how often each word appears, you will find a strange and universal pattern known as Zipf's law. The pattern is this. The most frequent word will appear approximately twice as often as the second most frequent word, 3 times as often as the third most frequent, and so on. In English, this means a few tiny, boring words like the, of, and a do an incredible amount of the work, while the vast majority of the interesting, content-rich words in the dictionary are used very rarely. This pattern, which holds true for every human language, is thought to reflect a principle of least effort. It is an incredibly efficient system. We rely on a small, automated toolkit of grammatical words to build the basic chassis of our sentences, and then we slot in the rarer, more specific, and more effortful content words as needed. Linguists and cognitive scientists debate whether this pressure for simplicity is primarily about making language learnable for a child, or making it efficient for an adult in the heat of conversation. In all likelihood, it is both. The child's need for a learnable system and the adult's need for an efficient one are two forces pushing in the exact same direction, shaping language into the elegant combinatorial machine that it is. This machine doesn't just give us the power to describe the world we see. It gives us the power to build the world we experience. The very structure of the language you speak can, in subtle ways, shape the way you think. This elegant combinatorial machine that we call language is not a neutral tool. It's not just a passive mirror that reflects the world as it is. The very act of learning a language, of adopting its unique vocabulary and its particular grammatical rules, shapes the way your brain processes reality. The tool you use to build your thoughts ends up influencing the architecture of the thoughts themselves. This leads to one of the most profound and personal questions in the entire story of language. Does the language you speak shape the way you think? This idea is known as the Sapir-Whorf hypothesis, named after the two early 20th century linguists, Edward Sapir and his student Benjamin Lee Whorf, who first developed it. The hypothesis comes in two flavors, a strong version and a weak version. The strong version, known as linguistic determinism, is the more radical and cinematic of the two. It claims that language acts as a prison for the mind. The categories and structures of your native tongue, it argues, determine what you are capable of thinking. If your language has no word for a concept, you simply cannot think that concept. This was the idea behind the old, and now largely debunked, popular myth that Inuit peoples have hundreds of words for snow, and that this allows them to perceive a winter world that is simply invisible to the rest of us. Today, this strong version of the hypothesis is almost universally rejected by linguists. We are not prisoners. We can always invent new words, borrow terms from other languages, or use metaphor to express new ideas. Our thoughts are not locked in a cell made of grammar. But the weak version, known as linguistic relativity, is a much more subtle and powerful idea, and it is supported by a growing mountain of scientific evidence. This version doesn't claim that language is a prison, but rather that it is a guide. It argues that the language you speak influences your habits of thought. It carves out certain well-worn paths for your attention and perception, and while you are perfectly free to wander off into the conceptual wilderness, you are more likely to stick to the easy, familiar trails. Your language trains you to pay attention to certain things while ignoring others. Let's look at some examples from modern experiments. Take color. In English, we have one basic word for blue. In Russian, there are two: goluboy for light blue and siny for dark blue. They are not considered shades of the same color, but as two distinct colors, just as we would see red and pink. In experiments, Russian speakers are shown 3 squares of blue and are asked to pick which of the bottom 2 squares matches the color of the top one. When the 2 bottom squares are different shades of blue, but both fall into the same Russian category, both are siny, for example, the Russian speakers perform the same as English speakers. But when one square is goluboy and the other is siny, they identify the correct match significantly faster. Their language has trained their brains to be more sensitive to that specific categorical boundary. Or consider space. In English, you use egocentric coordinates. The cup is to your left, the tree is in front of you. But in the Aboriginal language, Gugu Yimithir, spoken in Australia, they use absolute geographic coordinates. They would say the cup is north of you, the tree is to the west. To speak their language, you have to know which way is north at all times. As a result, its speakers have a sense of direction that seems almost superhuman to us, because their language forces them to be constantly oriented in geographic space. The effects can even be seen with something as abstract as grammatical gender. In Spanish, the word for bridge, puente, is masculine. In German, it's die Brücke, which is feminine. When speakers of both languages were asked to describe a bridge, the Spanish speakers were more likely to use words like strong, long, and sturdy, while the German speakers used words like beautiful, elegant, and slender. The arbitrary gender assigned by their grammar subtly nudged them towards different metaphorical descriptions. Perhaps the most dramatic and controversial example comes from the Piraha people of the Amazon. Their language is famous for what it lacks. It has no fixed color terms, no recursion, according to some analyses, and, most strikingly, no number words beyond 1, 2, and many. Experiments have shown that the Piraha have great difficulty in tasks that require them to keep track of exact quantities. Their language, which has no need for precise numerosity, has not prepared their minds for that cognitive task. The exact strength and domain of these effects is one of the most hotly debated topics in modern psycholinguistics. Are they just small, quirky lab effects, or do they point to fundamentally different ways of experiencing the world? The modern consensus is that language is not a prison, but it is a lens. Each one of the world's 7,000 languages is a unique tool for carving up the world, for categorizing experience, and for directing our attention. Each one is a living testament to the incredible diversity not just of human culture, but of human consciousness itself. The language you speak acts as a lens, focusing your attention and shaping your perception of the world. But for this entire journey, from the first grunts of our ape-like ancestors to the complex poetry of the Ice Age, we have assumed that the light passing through that lens is made of a single thing: sound. We have equated language with speech. And this, it turns out, is one of the most profound and persistent misconceptions of all. Speech is not language. It is simply one channel, one modality through which the deeper, more abstract system of language can be expressed. If that channel is blocked, our linguistic instinct is so powerful, so fundamental to our nature, that it will simply find another way. To see this in action, we need only to look at the story of sign languages. For centuries, in a world dominated by the hearing, signed communication was tragically misunderstood. It was dismissed as a crude and simple pantomime, a collection of ad hoc gestures, a poor and broken substitute for the richness of real spoken language. Deaf people were often considered intellectually inferior, a prejudice rooted in the simple fact that their language was not made of sound. But in the 1960s, a linguistic revolution began, led by a scholar named William Stokoe. Stokoe was one of the first to look at the American Sign Language, ASL, not as a set of gestures, but as a formal linguistic system. And what he found would change our understanding of language forever. Stokoe and the linguists who followed him proved that sign languages are not pantomime. They are not signed versions of the local spoken language. The grammar of ASL, for instance, is completely different from the grammar of English. They are fully formed, independent, and incredibly complex languages in their own right. They have every single structural component that spoken languages do. They have their own phonology, a system of basic units. Instead of sounds, these units are composed of parameters like hand shape, the location of the sign in space, its movement, and the orientation of the palm. A tiny, subtle change in one of these parameters can completely change a word's meaning, just as the difference between the sounds B and P can change bear to pear. They have their own complex grammar, a syntax that uses the space in front of the signer to create intricate relationships between different parts of a sentence. They have slang, regional accents, and even their own version of tongue twisters, rapidly produced sequences of signs known as finger fumblers that are devilishly difficult to execute smoothly. They are, in every measurable way, true and complete human languages. The final definitive proof came not from linguistics, but from neuroscience. When researchers put native deaf signers into brain scanners and watched their brains as they processed sentences in their language, they made a stunning discovery. The parts of the brain that were working the hardest were not the areas for processing visual or spatial information. The heavy lifting was being done in the exact same regions that hearing people use to process spoken language: Broca's area, the engine of syntax, and Wernicke's area, the hub of meaning, both located in the left hemisphere of the brain. The implication of this is breathtaking. The human brain, it turns out, has an abstract language faculty that is modality independent. It doesn't care if the information is coming in through the ears in the form of sound waves or through the eyes in the form of moving, articulated shapes. It recognizes the underlying pattern, the syntax, the symbols, the combinatorial structure, and it processes it as language in the exact same cognitive space. This proves that language is not a system for our mouths and ears. It is a system for our minds. It is an abstract piece of cognitive software that can be run on different biological hardware. Some researchers are now even exploring whether growing up with a visual spatial language confers any unique cognitive advantages, for instance in tasks involving spatial reasoning or mental rotation. The story of sign languages is therefore not a footnote to the story of language. It is a profound and beautiful conclusion. It is the ultimate demonstration of our brain's incredible plasticity and our species' deep, unshakable, biological instinct for language. It shows that the drive to connect, to build a shared world of meaning with others, is so fundamental to our nature that if the riverbed of sound is blocked, that powerful current of human thought will simply carve a new channel, turning the hands into a tongue and the space between us into a vibrant, living conversation. The story of sign language proves that the human mind will find a way to speak, regardless of the medium. The channel can change, but the linguistic instinct remains. And as you lie here, now, listening to my voice through a small, glowing device, you are living through the most dramatic change in that channel since the invention of writing. We are in the middle of a third great linguistic revolution, the shift into the digital age. For thousands of years after writing was invented, the world of language was neatly divided. There was speech, the fast, informal, interactive, and emotional communication you had with people face to face. And there was writing, the slow, formal, and permanent communication you used for literature, law, and history. The internet, and specifically the mobile phone, has completely demolished that wall. We now spend a huge portion of our day communicating in a bizarre and historically novel hybrid. Text that behaves like speech. We type as fast as we can talk, in a continuous, informal, back-and-forth conversation. Many people will tell you that this is destroying the language. They will point to the abbreviations, the lack of formal punctuation, the slang, and the typos as signs of a linguistic apocalypse. But is it decay, or is it adaptation? Are we losing complexity, or are we gaining a new kind of communicative richness? Think about what is lost in this new medium. When you speak to someone, your words are only a fraction of the message. The rest is carried by your tone of voice, your facial expressions, your body language. All of that is stripped away in a simple text message, leaving the words emotionally naked. And so, we innovated. We reintroduced gesture and tone into our writing. We use creative punctuation, like the ellipsis that implies a thought trailing off, or the exclamation mark that adds excitement. We developed a rich system of abbreviations and slang that signal our membership in different digital tribes, and most powerfully, we invented an entirely new visual language. Linguists are now seriously studying emojis as an emerging gestural system. These tiny pictures are not just decorations. They are doing real grammatical and emotional work, adding the layer of non-verbal information that the text itself cannot carry. But even as we adapt to this new ecosystem, a far more profound change is on the horizon. The rise of artificial intelligence, and specifically large language models, represents a turning point in the history of communication. These systems, the products of a field called computational linguistics, have been trained on a vast ocean of human-generated text, books, articles, conversations, a significant portion of the entire internet. They are pattern-matching engines of unimaginable scale, and they can now produce text that is often indistinguishable from that of a human. We are, for the first time, beginning to outsource our most uniquely human skill. Linguists, sociologists, and philosophers are currently in a heated debate about the long-term consequences of this digital shift. What does it mean for our own minds when we rely on a machine to compose our emails, write our essays, or even craft our emotional apologies? Are we creating an incredible new tool that will augment our own creativity? Or are we running the risk that our own linguistic muscles, deprived of their daily workout, will begin to atrophy? We are the first generation to be faced with this question, and the answer is yet to be written. Our journey tonight has taken us across 7 million years. We started in a Miocene forest, listening to the simple, ancient calls of a creature that was not yet human. We saw the slow shaping of the body, the rewiring of the brain, and the invention of the first tools. We sat by a fire with Homo erectus and heard the first stories. We stood in awe of the modern voice and mind of our Ice Age ancestors. We saw one language shatter into thousands, and then learned how to piece those fragments back together. It is an unbroken chain. Language is the software that runs on the hardware of our brain. It is the operating system of human culture. Without it, there is no history, no law, no science, no art. There is no shared imagination, no us. It is the tool we use to build our collective reality, and the lens through which we try to understand our place in the universe. It is the beginning and the end of what it means to be human. And so, our long journey through time finally comes to a gentle rest, right here in the quiet comfort of your own room. The echoes of those ancient voices, from the first primate call to the complex chant in a painted cave, all fade into a soft and distant hum, a quiet background to the steady and simple rhythm of your own breath tonight. Every word ever spoken, every story ever told, has led to this moment of stillness, to the silent language of your own mind as it begins to drift towards sleep. You are the current living chapter of this incredible, unbroken story, a story that is carried not in our bones or in our tools, but in the quiet, invisible miracle of the words we share. Let those words now dissolve, let the images fade, and allow your mind to float on that quiet, ancient stream that flows ever onward towards the new day.